Anton, are you starting?
Yes.
Good to see you, by the way. I wish you could be here.
Yeah, pleasure to meet you online this time. Let us know when you start.
Not this time. Are you ready to go, Rainer? Okay, so Rainer's ready. Are you playing the intro video thing, or are you just going?
No, it's live.
Is that?
Live.
We're live. Fantastic. Wonderful. Well, welcome to AGI-24 workshop on interpretable natural language processing. I did not know I was going to give an intro, so I will hand over to Anton Kolonin, who's our esteemed lead for this workshop. And so Anton, please present. You're up on the screen here in the room. You can see the audience. Anybody in the audience, if you've got questions, we do ask you come up and use the mic just so that it goes out onto the stream and they can hear. All right, fantastic. I'm going to mute here on this screen for now. Lilu will be in the room watching the laptop, and she can unmute and help with mic and anything else that you need. So, welcome, thank you, and Anton, over to you.
Okay, hello everyone. Let me get started with the overview of the work that me and my co-workers from various projects have been doing in this direction for a while. So we are going to talk about the subject of interpretable natural language processing. The main idea of the interpretable natural language processing is that we are building the language models based on interpretable structural knowledge, which can be called semantic graphs, or it can be called knowledge graphs, or it can be called ontologies. And when we are talking about knowledge graphs or ontologies or semantic graphs, we mean that the sorts of semantic relationships might be quite different, involving completely semantic relationships between the entities and including grammatical relationships between the tokens. And of course, these all sorts of links connecting semantic entities and grammatical entities, like tokens, phrases, letters, punctuation marks, and so forth. And the first question which comes to my mind when we start talking about the interpretable natural language processing or interpretable language modeling is, why do we need this stuff in the era of large language models, deep learning, GPT stuff, and so forth? So why do we need all that while the Turing test is passed long ago, and we now have all sorts of GPTs and GPT-like systems capable to provide the conversational interfaces with amazing quality, comparable to perception, from perceptual perspective, comparable to the human interactions? And the answer, in my view, is that it is fine as long as you are using these LLM and GPT systems for entertainment, for fun, for some creative activities. But when you need to actually put it into the business, and when you need actually to make money and make business impacting decisions based on this, you are in trouble because of the thing called hallucinations. And here is the slide which provides how the #1 in the business intelligence world company called Palantir is approaching the problem of hallucinations. In fact, Palantir is #1 company in the world doing business intelligence for military, government, business, all sorts of enterprises in the United States and worldwide. And he is using this company is using LLMs and GPT-based applications. So not GPT, but transformer-based applications. And they face hallucinations, and they see it as a problem, and they have a bunch of ways to solve this problem. And here is the graph depicting how they are using it. So if you look at the top, we see that the general framework of using LLM and transformer-based natural language interface is that we are creating some context for the query or prompt, and then we have some query, and then we have response generated by the system based on the prompt and the query. Okay, so the query is interpreted by the undergoing inference in context of the prompt, and then the response is based on that, and the response may be providing some hallucinating stuff which is not related to some real world. In order to minimize the effect of this, there are three basic ways that the company is doing. First of all, they are doing something that can be called ontology augmented generation, where they either put ontologies into the prompt in some way, or they put these ontologies into the query. Okay, so they can do sort of ontology augmented generation when the response by the LLM is generated based on either ontology augmented with some prompt, or the prompt is having the specific piece of the or specific set of ontological relationships or knowledge graph structures specific to the context of the query injected into the body of the prompt, and then the query executed in the context of this prompt is actually bound to the ground of the piece of the knowledge graph, guiding or narrowing the focus of the answer. That's the one way. Another way on the right is what we have, and by the way, I think that Ivan may talk something related about this, telling how this work helps to make answers by LLMs to be more precise based on the ontologies that are deriving these answers generated by LLMs. Another approach intended to filter the different responses which can be generated by the LLM might be somehow further communicated by Victor and Zahar in some later talk today. And in this case, instead of injecting logical relationships into the prompt or query, we rather first generate the response by a system based on the initial prompt and query, or we can have multiple responses based on different by the temperature setups. But then we can do some filtering, trying to see which of the responses are better matching to specific knowledge graph context, which is or ontological relationships which are actually trying to keep the answer within the subject of the question. And interesting approach number 3, which is implemented by the Palantir, is that what they call ontology-based grounding or knowledge graph-based grounding of the LLM. So what they do, when they are training the LLMs, they are training LLMs not based on the texts, raw texts, but they somehow inject the semantic relationships or particular pieces of structured knowledge into the text. So the text is interlaced with what they call grounding functions, or in some other companies these grounding functions called oracles. For example, in the OpenCog system it is a bit reverse. So in the OpenCog system you can have grounded nodes within the semantic graph, and these grounded nodes may be implemented deep neural networks. In some projects it's called oracles embedded into the semantic graph, but here it's quite opposite. We have a deep learning network, and then we have these semantic oracles or semantic predicates grounding the text learned by the LLM. So what we see here is that in order to do the inferences based on the transformer-based systems or LLMs, we still need to get the ontologies or structured knowledge, how you call it. And then the question arises, where you get these ontologies and semantic graphs and knowledge graphs. On one hand, it seems like transformers and LLMs make us to get rid of the supervised learning. We can just get a bunch of text and do just supervised learning based on them and create these nice large language models. But on the other hand, in order to get these large language models applicable for practical business needs, we still need somehow to get these knowledge graphs and semantic graphs or ontologies in order to make the answers precise in one of the ways that I have just communicated. So now let's talk about how we can use these ontologies or knowledge graphs for language models, or how we can learn them, and I will just give a few examples on practical applications and some theory, and then I will let other speakers to tell about their work in this context. So first of all, a bit of theory. Let's talk about the structured knowledge or symbolic knowledge in a way that we are not bound to old plain vanilla semantic graphs where you have just nodes and links or you have logical predicates. Let's talk about them in a novel or modern way where every link between the symbols or where every semantic relationship in a semantic graph or a knowledge graph or where any predicate may be probabilistic and being subject of inference in terms of fuzzy logic or probabilistic logic or soft logic or non-axiomatic logic, as in case if we are using P1's non-axiomatic reasoning system. And in this case, the larger world of the language modeling or language processing might look like is shown on this slide. And you can think about the slide in terms of Daniel Kahneman's System 1 and System 2 thinking. On the left, you can see what Daniel Kahneman refers to System 2. And the System 2 is symbolic reasoning, which is slow to do the inference, but it is fast to learn. And it operates at symbolic level. And on the right, you can see what might be called System 1, which is fast for doing inference, but really hard and slow to learn. And what we see here is that in both cases, we can deal with graphs, and we can deal with probabilities, or weights, where the weights are associated with the links. And these links might be either the links between the specific semantic nodes on the left, or they may be just the links between different artificial neurons in the multi-layered neural network. And in both cases, you can figure out how particular distributions of weights may be causing specific inferences based on these weights. With only difference that on the right, all nodes are anonymous. So, for example, if, like on this slide, we consider the task of the part of speech tagging, the input layer corresponds to symbols or tokens in this case, like words in the sentence, and the last layer corresponds to parts of speech, again symbols, like now, here. And when we are doing inference through the layers, we can somehow figure out that particular word, like word saw, here in the context of the words I saw the rusty soil, corresponds to noun. And we are speaking about the second saw, because obviously the first appearance of saw is a verb. And on the left, we can see that we can do the same with similar distribution of weights on the links, but every node in the graph on the left corresponds to particular semantic entity type. Like in terms of the link grammar, the formalism of interpretable language modeling, use it for this example. The second layer, like SP, OS, DS, A, and G, is corresponding to different types of grammatical links. And the second layer corresponds to what is called in link grammar formalism disjunct. And in these disjuncts are just joining combinations of particular links which may be corresponding to either nouns or verbs or adverbs and so forth. And if you look into this larger world from this perspective, you can think that we can learn we can artificially engineer the models in an interpretable way and then somehow transfer these models into the deep neural networks for doing faster inference. Or you can do the opposite way. You potentially can learn the anonymous nodes in a deep language model, a multi-layer neural network using the deep learning, and then you can explain this knowledge, expressing it into the structured way. So you can do the knowledge transfer in either direction, and you can perform explanation of the models not after the answer is generated, like in typical explainable AI, so to speak. Right? In explainable AI, the idea is that when you have the answer of the system generated, then you later on can explain the reasons why the answer is generated. But in the interpretable approach, instead of explaining the answer, you can explain the model. You can actually interpret the model before any decision is made, and you can actually, before applying the model to the production, you can investigate and inspect the model to make sure that the knowledge that is contained in this model is reliable, and then you potentially can engineer this model, you can edit it, you can amend it, you can correct it, and then potentially you can transfer it into the distributed representation in order to do the inference. One way for doing this kind of interpretable modeling is, as I mentioned, provided by the link grammar formalism. It is described in multiple papers and books. The problem, and later on I will show some brief examples of using this approach. The only problem of this approach, to me, is that is covering only the grammatical piece of the knowledge. So the link grammar formalism doesn't have any way to ground the grammatical structures to the semantics. And that's one of the problems why the link grammar cannot be completely used for building some natural language applications, while I will still try to show some examples. Another approach that we are developing in my Aigents project, in source Aigents project, is that we are building the language models in terms of what is we call deep patterns. Any deep pattern is a graph, directed graph, and it is weighted graph. And this weighted directed graph might, note that the graph is not is directed, but it is not it is not hierarchical. So every node may have as many parents and as many children on this graph, and there are weights between the links. And distribution of weights across the links correspond that some of the links that unify or join different interpretable or symbolic entities like tokens, cold, heat, frustration, anxiety, and so forth, and abstract entities like nouns, verbs, effects, procedures, drugs, they may be joined by anonymous concepts or anonymous nodes. And these anonymous nodes are served as either soft logic conjunctions or soft logic disjunctions based on the structure of the weights distributed across the links that are connecting them to either incoming links or to outgoing links. And this way we can build different applications, starting a natural language application, starting from classification, like we can use the large, very large, blown up deep pattern to identify particular categories like healthcare or English language, like the whole ontology and grammar of the English language is a pattern on itself, and whatever is matching this huge pattern can be said written in English language, and more specific patterns may be corresponding to something written about healthcare. And then you can do more specific tasks like pattern matching for specific cases or relationships, like something is being treated with something, some symptom maybe here, maybe treated with particular drug or particular medicine or particular medical procedure. And finally, we can do very precise extraction of the entities attributing the particular attributes of the relationship. Like after we have identified a particular piece of text corresponding to a particular semantic relationship, we will then extract the entities, either named entities or names of the particular pieces of this relationship, like for the relationship of treating something with something, we can extract the reporter, we can extract the diagnosis, and acting substance and reliability and effect, positive or negative, and so forth. And here is an example how we are using it. We have the thing which is called deep pattern, and deep pattern may be described in this sort of language, and then we describe the pattern in the language that is in the middle of the slide, and then we perform the convolution of this pattern with the raw text. We effectively get the structured relationship which connects different concepts in one relationship. Like we take the text from some medical inventory, we have the pattern, and we get attributions of this particular medical article used in healthcare. Another example that of using this interpretable modeling in our work is interpretable sentiment analysis. So here is the story of applying our work for Singularity DAO project a while ago for using news analysis, performing news analysis and sentiment analysis in particular for market prediction. What we have tried to do, we have tried to use sentiment analysis to detect patterns on news media corresponding to either increase or decrease of the crypto currency prices. And what we have started with, we have started and explored about 20 different models available open source at that time, and one of the models was FeedBERT. That's a BERT transformer, the LLM, which was trained on the financial data corpus. And we have tried our interpretable model based on these deep patterns. And what we have found that out of the box, FeedBERT and our out-of-the-box model were providing the same accuracy at level of 0.333 and something like that. And at that situation, we have realized that we can hardly improve the field without of getting the core training corpus much larger than we have that was used to build this FeedBERT model, and we just didn't have money and resources to create such larger corpus. So what we did, we were using our Aigents model, where we were able to actually work manually on creating the patterns, extending the set of the out-of-the-box patterns for sentiment analysis, extending them for different figures of speech and the typical phrases and the textual patterns corresponding to financial domain, and after a few days of tweaking the library of patterns, we were able to increase the accuracy up to 0.58 or something like that. And here is an example of how we use this sentiment analysis in our smart newsfeed analysis, where Aigents newsfeed aggregator not only extracts the newsfeed from the any raw text data like RSS feeds, news websites, Telegram, chats, and so forth. It can extract any topics of interest based on these patterns, but in addition to extracting the news corresponding to specific topics, it can also detect the positive or negative sentiment from this topic and mark like what is green is more positive, what is red is more negative, and if you see some topic under the both red and green, you can actually see to which extent this topic is mentioned in news media is either positive or negative or some combination of that. Another example of how we use this sentiment analysis is Telegram chat moderation. Like on the left you see some chat in some test chat, and you see that some messages are more or less negative and some messages are really negative, like and they are subject to be removed if too much negative sentiment or insulting speech is appearing in the message in the chat. So the bot engages, is trying to engage, the bot using this sentiment analysis is trying to engage users of chat into the positive communications. Like if bot detects the sentiment is negative, it smiles. If bot detects that sentiment is negative, the bot makes a sad face. If the sentiment is kind of rude, the bot makes a red face and wide open eyes. And also, if something is really bad, the bot reports such messages to admin. And if something is really bad, sounds really bad, then the bot even removes the messages from the chat, in addition to reporting these messages to the user, so to admin user. On the right you see the bot, Aigents bot, monitoring the specific chat, and the bot is reporting to admin, who is the owner of this bot and the owner of this chat. Another example of using interpretable sentiment analysis for Chinese has been done by one of my students, and it is shown that he has compared a bunch of different models, sentiment analysis models, and our model transferred to Chinese has appeared to be superior. Another interesting work that I will let cover Anna in her later presentation today is about exploring cognitive distortions. So the cognitive distortions are particular states of mind studied by cognitive psychologists in cognitive behavioral therapy. It is used primarily in healthcare for improving the health states of the people. And I will give some examples later on, but the examples that that we have used also at SingularityNET project has shown us that finding these cognitive distortions in the social media text can provide really good predictive signals for the price changes on the cryptocurrency markets, and even better predictive power has been shown in respect to the volumes of the trade. So almost every change of the trade count or trade volume on major cryptocurrencies is actually anticipated by the specific combinations of the cognitive distortions. And finally, what we have tried to do in the scope of the SingularityNET project, we have tried to build the market making strategies for trading on the different sorts of cryptocurrencies, primarily Bitcoin. Some of the strategies on the right were just completely financial, and they were not using any predictions, and strategists on the left were using our predictor of the price based on this sentiment and cognitive distortions metrics evaluated by the approach that I have just described based on these patterns, deep patterns. And we have found that when we are using the prediction of the cognitive distortions and the sentiment associated with the price, we can build predictors which can significantly improve the performance of the trading. Like almost every strategy on the right without using our social media based predictor provides negative returns, so everything is in red. And half of the strategies that we have used based on our predictor provide substantial profits, and the profits are larger. The profits for the first half of the strategies is twice larger than the losses for the other half of the strategies. So we have found that that's interesting. And finally, this case is the result of the work that we have performed together with Sberbank of Russia. We were developing the application of such cognitive distortion analysis and emotional analysis of the communications between the psychotherapist and the user, where our technology could be helping cognitive behavioral psychologists to define the diagnosis and improve the accuracy and performance of the diagnosis and respective psychological care. I will let Anna talk more about the details of the way the cognitive distortions can be explored, and I will move to some other applications based on the link grammar. So let's say we have the link grammar language model created somehow, and I will later tell a few words how we can actually get these models. But once we have the link grammar language model in terms of the link grammar dictionary somehow obtained, then we can build natural language applications like parsers, which can build the parsers of the languages and natural language text which can be used further for relationship extraction. We can do the text segmentation or applications like segmenter, which can take just input from the output of the text, speech to text translator, which gets just stream of words without punctuation, and then it can translate the chunks of words into the segments which are corresponding to specific sentences or phrases, and so the readable text can be obtained. And finally, the generator, which can just take the words from some retrieval operation, and then these words can be transformed into the grammatically valid sentences. So here are examples of our experiments with the grammatical language generation based on the link grammar. So we see some reasonable performance of generating sentences based on the link grammar. We further explored how we can build the question answering systems based on this generator. So when we send the query against the text, we find the words that are found in this text. So that's retrieval of the words that have to be communicated to the person who is asking the question, and then instead of, like in retrieval augmented generation with LLMs, when you get some answer from whatever query you make by the retrieval system, then you augment your response with the LLM. So you send these words, or you send the answer to the LLM, which builds the natural language text. So instead of using LLM, we can just send the words that we have got from the query to the generator, and then it builds up the grammatically valid sentences in the context of the query. But still the question remains, how we build these models, how we build these ontologies, how we build these formal grammars represented in terms of some structured knowledge, some grammatical links and relationships between the grammatical nodes to semantic nodes. And the question, to answer this question, we need to consider three processes that are parts of the learning the language model in a structured way. And these three processes are clustering, segmentation, and parsing. And the problem, the major problem that we see in applying this approach systematically is that you can hardly separate them from each other. So they have to be all pretty well connected in the single unified process. For instance, you can have the clustering at different levels. So at some level you can have clustering of different writings or typefaces of the same symbol. Like different source of H and different source of I are the same. Further, you can cluster these symbols from the perspective of either whether they are vowels or consonants. Then you can cluster the words based on their grammatical meanings, and at the same time you cluster the words based on the semantic meanings. And the grammatical might be different, like plurals or male or different genders or different contexts. So every word or every grammatical unit can correspond to multiple hierarchies, multiple ontologies from different semantic and grammatical perspectives, on one hand. On the other hand, when you are doing the segmentation, you're also doing segmentation at different levels. So you have the subword segmentation, you have the text, we have the sentence segmentation, word-wise segmentation, then you have sentence-wise segmentation, then you have paragraph-wise segmentations. And finally, you need somehow to connect the meanings of these different pieces. You need what is called parsing. And the parsing also might happen at different levels of this segmentation. Like, for example, you can have the parse of the word, having the ending of the word associated with the root of the word, and then you have parsing at the word at the level of the sentence, where you have the subject, object, and verb linked in the same graph corresponding to the grammatical structure. And it can be shown that this parsing is not either between the pieces of the word, like subword units, or it is about the pieces of the sentence, like between the words. It is the same at the same time. Like, for example, at the top, you see the two different sentences in English which have the same meaning. It is impossible and it is not possible. And you can see that there are the same parsing graphs. But in one case, on the right, the parsing link connects different words, like not and possible, and on the left, in the English sentence, the parsing link connects to different subword units, like prefix in and root possible. And in Chinese, it is even more interesting because in Chinese the word segmentation is pretty vague. It is, and you can actually get the same sentence with the same meaning with different sentence segmentation. Like if you take the translation of the same sentence above in Google, it gets without of any punctuation, without of any spaces. But if you take GEBA tokenizer, it splits the same sentence into different, what can be called words in Chinese. But the structure, parsing structure, semantics graph representing the relationship between it is and not possible and impossible is always the same, like it is drawn by these links. Now let me get a final bit of theory to move on how we have started doing some studies in this area. Found that besides the conditional probability used in most of the applications in language modeling nowadays, There is an interesting metric called uncertainty, or transition of freedom of transition. And in order to get the idea of this freedom of transition or uncertainty, can be given for you when you are trying to do autocomplete on your Google query search. Like for example, if you are entering how are, you have just two options. It can be either how are you, or it could be either how are things. So Google doesn't have more options. It just has two options: how are and then you, or how are and then things. So the freedom of transition in terms of or uncertainty is pretty low. There are just two different states that can be obtained after how are. And if you enter how many, you can find that there are many states or many transitions to make after the how many following the sequence of tokens. And here is an example. If you get this down to different numbers or probabilities based on what can be found in Google, for example, and the numbers here are from Google. You just can enter the word. You can enter the word and count the number of the responses found based on these combinations of words. You can find that after how there are just two different states. So the freedom of transition from how is 5, and if you enter how many, then the freedom of transition is 4. And the numbers of millions of different cases correspond to different probabilities. You can compute conditional probabilities of people, times, and countries after how many. And if you consider how are, then there is just you, and thing is just almost not countable. On the previous slide, you can see things, but in terms of probability, the things is just negligible. It's just around 0 here, while u is 132 million. But the freedom of transition here is 1. So after how are, we have freedom of transition 1, and after how many, the freedom of transition is 4. Long story short, we were using these two different metrics for probability and freedom of transition for doing unsupervised text segmentation, which is the first step in order to build the languages of symbols, which can further use for the building larger hierarchies of the grammatical graphs with grammatical and semantic relationships between them. So what we have tried to do, we have tried to see if we can separate or segment the text into the words based on these conditional probabilities with different sizes of n-grams, computed from the left to right and from the right to left in the text. So blues are left to right, oranges are from right to left, and long story short, using the conditional probability, we were not able to correctly identify most of the tokens. Like some words were just split into pieces, like proper name Tom is cut into pieces, or the punctuation marks like quotes, double quotes, periods, and colons were all glued up with the words. So the false positive and false negative didn't make it possible for us to do this unsupervised segmentation very properly. And we have started using this freedom of transition or uncertainty measure. We suddenly have found that we can do almost perfect segmentation. I will skip the slides corresponding to how we were studying the hyperparameter space to find the better parameters of the learning system. But the key point here is that we have found that in order to find these sweet spots of the hyperparameters, like thresholds for injecting the breaks into the sequence of tokens, or the n of the n-grams that we are using to compute these either conditional probabilities or transition freedoms, or different thresholds that we are using to cut off low probability transitions. We have found that we can find these parameters without of doing actually what is called AutoML based on some gold standard training sets. We have found that there are some universal metrics which are not quite dependent on the language as long as we have studied Chinese, English, and Russian. And if we take these language agnostic, so to speak, metrics, and we have optimized the maximums or minimums of these metrics for the parameters, tokenizing the space with these parameters, then the same parameters might be good for the proper tokenization. Two simple metrics like compression factor, like whichever makes the compression of the language corpuses better is the best for human friendly or human or nice looking for human tokenization. And another metric is anti-entropy. It's a metric opposite to the entropy. Again, if we maximize anti-entropy, then this set of parameters, regardless of the language, provides the best tokenization. So here are the studies that we have run. That to prove this. So on the top row we can see the English data sets. In the middle row we see the Russian data sets, and at the bottom we have Chinese. And all diagrams correspond to different corpora of different sizes. And on each cell, on vertical axis, you see the F measure of tokenization. And on the bottom axis, horizontal axis, you can see the value of one of the metrics. We have considered 4 different metrics here, and the leftmost two are anti-entropy and compression factor. And we see that for most of the English and Russian corpora, we see semi-linear dependency between the F measure and these metrics. For Chinese, it is not quite clear, but what we have found that the correspondence between the metric and the F measure increases over the size of the corpus, the strength. So what we have concluded is that given the nature of the Chinese language, you need to just get larger corpora to see this correlation. And here are the numbers that we have got in our paper published in the MNLP conference a couple of years ago, that we have got 1.0 F measure tokenization of matter for Russian, almost 1.0 for English, and somewhat worse for Chinese. But I guess that was because of the small size of the corpus that we were using for training. Also, we have used this learning in order to get, okay, I will be wrapping up soon. So we were able to do this transition freedom based graphs learned from the training corpus in order to get the right learning of the categories, grammatical categories of the symbols, like we have got vowels, we have got consonants, we have got numbers, we have got all sorts of punctuation marks or special symbols into distinct clusters. We have used another approach I presented on the previous Interpretable Natural Language Processing workshops previous years. We have done the work of doing the same for English language learning using link grammar formalism. We were able also to use to learn the human friendly, so to speak, and aligned with human perception grammatical categories in hierarchies. Like we were able to learn the hierarchy of relationships in family, in the text based on the family, relationships of different tools, and instruments in the text corresponding to tools and instruments. And finally, another example of our work in this area is building instruments for data-driven conversational intelligence, where we can actually build a graph of the knowledge, and you can build the conversational interface where for searching particular subjects, like you can search for particular locations in a country or in a city, or where you can search for particular items in the store while doing shopping, and this and you locate these items using the automatic drill down of the hierarchy of the relationships in the space, driven by different relationships on the links associated with particular search of interest in this graph. Like, for example, if we are looking for a restaurant, then like a particular restaurant has a relationship to particular kind of cuisine, it has a relationship to particular location, it has a relationship to particular category, and when you perform the search, your search is used, your text is used to get matches using our deep patterns to particular semantic concepts on each of these three directions, and then the system identifies the point in space which is corresponding to these concepts the best, and then still if there are multiple points in this space, all right, because the space might be six-dimensional and we have identified just three locations, three filters or three criteria, attributes of this point, then the system is capable to figure out what is the question to answer next, what is the attribute of the object of the searchable, of the object of the subject of the search to be identified next, and then the system asks the questions, and then you answer the question, and it gets more precise location of point in the multidimensional space, and after all, through the short conversation, you can actually locate the item during the conversational interface. In this case, that's fast food restaurant in the United States. This is done without of the LLM, but if you want this conversation to be more nice or more funny, you can augment this conversation with retrieval or augmented generation, the way retrieval augmented generation is working right now. So here is example of how we actually use the language generation based not on the link grammar, but based on our deep patterns. So here you can see that you can have a semantic graph corresponding high-level concepts like nouns and verbs, lower-level concepts like body parts, interactions, processes, languages. Then difference. We can also have different languages in the same graph, right? So the conceptual space is joined and shared by different languages. But for each of the languages, you have different sets of tokens grounding this abstract space of the concepts to particular linguistic domains. And then when you perform some particular query, you have indication of, for example, the language you want to have your answer generated in. You have the particular context of which you want to use for performing particular action, like hand given in this case, and then you can specify the mood that you want your sentence to be generated in, and then spreading attention in yellow here, you can actually get the most probable, using the probabilistic inference, you can get, or spreading attention in the semantic network, you can get the most probable or most activated nodes, which can let you generate particular sentence in target language. So at this point, I'm going to drop my speech and let some questions go, if there are any. If there are any questions.
Does anybody have questions? I have a question. How do you create ontologies for growing and what type ontology do you use? RDF, RDFS, or OL?
Well, RDFS and or OL, these are just I would say, formal, so notations to write ontologies, right? So the major problem is actually get the content of the ontology and not write this, and then you can write it in any way. You can write it in OL, you can write it in RDF, you can write it in atomize or meta in OpenCorp, or you can write it in Turtle. So the choice of the notation for ontology is not a problem. The problem is how you actually grow it.
Thank you. What is your engine for create ontology? Можно спросить?
Okay, yeah, I see. So what is the so the engine for creating ontology? So across the line, across this talk, I was mentioning different projects. Okay, so in the project which was the most advanced in terms of ontology learning, what we were using was that we are using a minimum spanning tree parser, or we are using BERT in order to do the parsers. So what we were doing? We were building the parsers of the sentences, either using minimum spanning tree parser or using the parser based on the mutual information or contextual information extracted from the BERT. So we were training the BERT. The BERT was building the language models, unsupervised language models, or uninterpretable language models. And then for every sentence that we wanted to parse, we were just finding what are the contextual relationships between the every word in the sentence in the context of the particular sentence in the BERT. And then from the corpus of the text, we were able to get a bunch of parsers. So every sentence was parsed, and there were links connected to the sentence, and we were using the associations of links with every word as features for doing in the vector space. So instead of using the word embeddings, instead of using the link embeddings, we were using what is called disjunct embeddings. So every word was associated with a bunch of what is called disjuncts, and disjunct is just a conjunction of links, bunch of links. And then each word was just, and then we were just using agglomerative clustering. And using this agglomerative clustering in the vector space based on the disjuncts associated with this every word, we were using growing these ontologies. That was on one of the slides.
Thank you. Your ontologies is hierarchical clusterization, and what is predicates in your ontologies?
Okay, so that's a good question. So so far, all ontologies that we were able to learn are more taxonomies. So far, no real ontology with relationships and predicates have been learned. And that's the problem.
Thank you.
So still lots of work ahead.
We have a question from the audience here.
Thank you. I'm Scott David from University of Washington Applied Physics Lab. Thank you. That was a fantastic presentation. Or we?
Ask him, can you hear you?
Can you hear me? Can you hear me okay?
Yes.
Okay.
Yes.
That was a great presentation, very, very thought-provoking. I had a couple of questions, excuse me, a couple of linked questions, and where it's heading, the questions together are meant to get your thoughts on how we identify and quantify and mitigate the risks, the risks of the differentials between AI outputs and human expectations. So the quantification of these deltas, the differences between, your observations, we're trying to get something that resembles or replicates human interaction. And so the identification of differences, but let me move towards that. So the first question towards that is, how might traditional linguistics and language studies and the thinking of the different people who wrote different dictionaries, Webster wrote an American dictionary because he wanted to distinguish the United States from England, from the Oxford English Dictionary, and Samuel Johnson's dictionary also helped to form language as a standards for communication in a society. So how might traditional linguistics across different cultures, are they already being normatively cross-referenced in your work? Is the linguistics exercises prior to AI and prior to these large network systems of information, we had the study of languages and linguistics, and are some of those structures, because those were about identity, about human identity, might the resurrection of some of those linguistic models help us understand some of the ontology gradients that we're experiencing?
I don't have a sound answer to your question. I can just reply saying that, in my view, the modern direction of the AI development in natural language processing is, or was at least till the very last days, moving away from the traditional linguistics. Like the modern discourse I often hear is that, guys, look, you are saying about the rules, you are saying about the formalisms, you are saying about dictionaries, but you will not ever be able to end up with finite set of rules. You will never be able to end up with finite set of dictionaries. But we just take the LLM large enough, and we just take the enough training corpus large enough, and look, we just have accuracy of next token predictions greater than you have with all your dictionaries and formal models. So that's the discourse that I often see. But are you sure that being able to predict next token is what you actually need? And whether the probability of the token is the real meaning of the human language? And I don't have easy answer on this question, unfortunately. I think, in my view, I think that in fact there is no disconnection between, as I mentioned at some point in the very beginning, if you end up with the formal models which take some probabilities or some priorities, like consider you have the dictionary, like you have the you have some synonyms, right? And you just, in typical dictionary, you just list the synonyms one after one. But let's say that in your dictionary you have some probabilities assigned to the synonyms, like one synonym is used more often and another word for this synonym is used less often. And then in fact you actually incorporate the same probabilities that are embedded into the deep language models. So I think that enriching the formal dictionaries and language models with the probabilistic information might actually bring them up closer to the conventional language models. And then you can, and if you could extract the uninterpretable knowledge from these language models learned unsupervisedly, you can actually make sense of your dictionaries and probabilities in these dictionaries.
Yeah, it's interesting the way you describe it. It raises the notion, it's like it takes two people to dance. And so it takes humans and AI to have the interactions. And the Gaussian distribution, the probabilities analysis is used by the systems, the AI systems and the human systems. And what it makes me think about is, maybe the hallucinations, we talk about AI hallucination, but maybe what we're really talking about is human hallucination of AI output. A moth has eye spots on its wings, that some of the moths have eye spots that look like eyes. Those evolved because the moths that had the eye spots didn't get eaten by the predators, probabilistically. And so the moth doesn't know that it has eye spots, but the predator perceives it as being a larger animal and doesn't eat it. Well, similarly, we have the LLM, other models don't know that they're outputting meaning, that it looks like eyes to us. It looks like text. It looks like it has ontology. It's computational. And so the humans that survived were the ones that saw a lion in the grass, even if there wasn't a lion in the grass. So it's called pareidolia, right? That notion of human projecting out, hallucinating the image. And the way you just described it, it made me think, there really is a dance of mutual hallucination of the system and the human. That's because it's a computational and an ontological system, maybe that interaction of those mutual hallucinations, describing the expectations of the system and the humans there, is probably going to be a source of future risk instruments, insurance type instruments, other people wanting to mitigate the risk of the hallucination having an offset, not having not being identical. Anyway, I love the way you are presenting the material and breaking it down. It really leads to a lot of these questions, and I really appreciate your presentation today. So thank you so much.
Yeah, thank you. Very interesting point. Okay, so if there are any questions, maybe we move ahead to our next speaker.
Would you like to take another question?
Okay, then Ivan, maybe you can present your work.
Oh, I think somebody's gonna present, I think.
Thank you. Hello, everyone. I'm glad to tell you about my research devoted to hierarchical multitask learning for knowledge injection into deep neural network. But I start not from natural language processing. I want to start from a common problem of distributional shift. This problem is a main problem for any area of artificial intelligence, such as computer vision, tabular data processing, and natural language processing too. I want to illustrate this problem with a beautiful example, which I take from in paper Invariant Risk Minimization. What difference between cow and camel? each sample in train set or in test set has a mixture of k features of object and some environment features. For example, you can see different environments such as grass or sand, but we know that k features which has a difference between cows and camels is horns and so on. For example, you can see horns on a cow. And our algorithm, our machine learning algorithm, have to build invariant correlations between target value and our features, and they don't find any spurious correlation. For example, if our algorithm finds spurious correlation, then all cows on sandy beach will be classified as camels, but this is false. And this problem is very important for machine learning, in particular for deep learning. So there are different research and research competitions devoted to this problem. One of them was robustness and uncertainty under real-world distributional shift. This competition devoted to uncertainty estimation and robustness to distributional shift in real world in three different tasks. One of them is weather prediction. This is a classical regression task on typical table of data, but a shift, distributional shifts, was represented by geography and time. Data for train sets and for in-domain development and evaluation sets were collected from tropical climate and from 2018 year, but special test sets which contains shifts, data shifts, which was out of distributional, were collected from polar and snow climate and from different time interval. And there are many solutions, many algorithms were proposed on this competition, but the first place was but the best algorithm was based on deep neural network with some techniques. Many algorithms was based on classical machine learning, but the first place was based on deep learning with some features. With ensembling, with special normalization between layers in deep neural network. This is based on self-normalizing neural network. And K feature of proposed solution was based on a hierarchical multitask learning. Why? As we know, neural network, we can represent neural network as hierarchy of learned representation. Deep neural network is hierarchy of layers, and each layer is learned representation. And if we use usual backpropagation, then neural network builds learned representation layer by layer. But we can help help neural network to build true hierarchy of representation. If we know some taxonomy devoted to our domain, if we know a hierarchy of domain concepts, then we can project this hierarchy onto a hierarchy of layers. For example, in this case, we can build simple taxonomies, simple ontology devoted to weather, devoted to temperature prediction. Our goal is prediction of exact temperature, but this is a fine-grained case of more coarse case. For example, temperature forecasting is a special case of classification of coarse temperature classes. And we can generate several tasks, several additional tasks on basis of our taxonomy. And we can create a complex loss function for this deep neural network, and each layer can learn corresponding additional task and position of layer correspond to position of concept in hierarchy. This idea, if we want to help our deep neural network to build a good hierarchy, this idea is based on some biological foundations. For example, we know that our semantic memory has some hierarchical organization. For example, well-known model of Collins and Quillian, which was proposed for semantic, which was based as foundation for semantic networks, can be used for a more efficient end-to-end learning of deep neural network. For example, our hidden layers are some feature learners. First hidden layer is more simpler, more abstract feature learner, and the next layer from first to last hidden layer builds more sophisticated, more task-oriented features, and last layer is classifier. We can project our ontology with special relations, hypernym relations, for example, and we can project special relations from ontology to relations between hidden layers in our neural network, and we can generate additional tasks. If we have ontology, then we don't need any additional annotations, additional manual labeling. Additional labeling for additional tasks can be generated automatically, which on basis on ontology. And in natural language processing, we have many prepared ontologies. For example, well-known WordNet as ontology of senses. Or if we tell about automatic speech recognition, speech-to-text representation, we can be built our neural network on basis of phonetic ontology. For example, if we want to build a language independent speech-to-text model, we can use pre-trained transformer. Transformer is deep neural network, but on fine-tuning stage, we can help transformer to find better phonetic representation if we account phonetic ontology. We know about high-level phonetic representations, but all phones can be divided into 3 classes, for example, vowels, consonants, and silents. And low-level classification on consonants and vowels can be generate more fine-grained levels, for example, fricatives, unround vowels, and so on. And if we use this hierarchy, if we project this hierarchy onto our Wave2 architecture using hierarchical multitask learning, then we reduce phonetic error for example, for low resource languages. If we have small train sets for fine-tuning, then using a priori information from our taxonomy, from our ontology, helps to build more robust solution. Yet another case is based on another taxonomy, linguistic taxonomy. As we know, if we want to build named entity recognition tasks, then we have to understand then named entity recognition task is semantic task. Named entities are semantic objects. But semantics is based on syntactical analysis, and syntactical analysis is based on morphology. So we can use this taxonomy of linguistic levels to generate automatically generate additional tasks for transformer encoder based named entity recognizer. For example, BERT based named entity recognizer. Our high-level task is named entity classification, but named entities are semantic objects which use syntactical information, and our mid-level task is dependency tree building, and our low-level task is part of speech tagging. This is morphological task. So our semantic task and linguistic ontology can generate 2 additional tasks: syntactical task and morphological task. And this multitask learning, hierarchical multitask learning, which is based on hierarchy of morphology, syntax, semantics, helps us to increase quality of BERT-based NER, and this approach, if we project our ontology into a hierarchy of layers in deep neural network, this approach helps us to build 2 main things, 2 main features. First feature is solving of vanishing gradient problem, because additional tasks for hidden layers of our neural network helps to build a vanishing gradient problem in a very deep neural network. Yet another useful feature is injection of hierarchy of domain concepts, and in this way we build more robust to distributional shift. We build solution which more robust to distributional shift, because we train our hierarchy of learning representation in such way then first layer representations learns more simple and more abstract additional tasks, which are common for many fine-grained cases, and only last layer learns high-level fine-grained tasks, but they are based on previous more abstract representation. So this is, in my view, this is universal framework for any domain into which we can use prepared ontology. For natural language processing, for speech-to-text task, we have natural ontologies. For tabular data processing, for example, for regression tasks, we can generate ontology on basis of next idea. Regression task is fine-grained, is a fine-grained case of hierarchical classification task, and so on. This is my key results using of hierarchy, from extracted from special domain-specific ontology helps neural network to build a good learned representation, and this helps to build more robust solutions. Thank you for your attention. Thank you for my colleagues from Mathematical Center in Novosibirsk Akademgorodok. I am glad to answer for your question.
Seattle, you have any questions? Ivan, I have a question. Do you have any vision on how would we get these ontologies constraining the learning process to be done? So do you anticipate there should be manual effort, like we are doing markup, human markup for training, supervised learning, then we, instead of doing supervised markup for supervised learning, instead of doing this, we have unsupervised learning, but we have these ontologies as extra input. Or there is some way to get them semi-automatically?
Thank you for your question. Hierarchical multitask learning is supervised learning, but we have a sequence of tasks. Our high-level task need to manual annotation, but if we use ontology, then we generate additional low-level tasks from high-level annotation automatically using this ontology. So we don't use any manual annotations for additional low-level tasks.
Is it kind of what is called curriculum learning?
I think that these are different things. For example, curriculum learning can be based on conception of difficulty of tasks. For example, we can start our training from not difficult task, and after from training epoch to training epoch, we can increase difficulty. Difficulty estimation, for example, in NLP, can be used from on basis of some formal criterions, or we can use special neural network to difficulty estimation. For example, we know about neural network estimation of text difficulty for scholarship and so on. We can reuse these solutions for difficulty estimation and for curriculum learning. Or we can estimate difficulty as syntactical difficulty, or difficulty of text can be based on simple length of text, for example. But if we use ontology and if we project ontology into neural network, this is not curriculum learning, this is another approach.
Okay, thank you, Ivan.
Thank you.
Seattle, do we have questions?
I think we're
Okay.
okay. If you want to continue.
Okay, thank you, Ivan. Then thank you very much for your presentation, and let's move to our next speaker, Victor or Zahar, who is going to present your work.
I'm ready.
Hello, let's go.
Okay. Good afternoon. My name is Victor. I would like to present a report about hallucination detector in RAG systems. Here, also Zahar Panimash as the main developer of hallucination detector. You know about hallucinations. It's a very difficult problem. LM often produce destructive answers, and it's crucial for business implementations. So you know about this problem. So I would like to go further, because all we know about hallucinations, and there are a lot of buzz in the internet about this difficult task. What is a typical RAG pipeline when you try to implement transformer neural networks in business units? You often want to split text on small chunks. Then you need a very good embedding model. Then you need a vector database. You need to build a search that finds snippets in vector database, and then finally only you use a large language model such as ChatGPT, GigaChat, YangGPT, Fractal GPT, Mistral, Gemini, and so on. And at the end, you got a final answer. But what are the common problems in a RAG pipeline? Here on the image, you can see emphasized as red rectangles. First is text splitter. you often destroy the structure of the documents when you try to produce smaller chunks. A second problem is usage of vector database, and finally, when you try to use a large language model that takes as input those smaller chunks that are stored in vector database, you got a final answer from broken structure. So this is the first source and the most often source of hallucinations, because you destroy a temporal structure of the documents. And what is the common solution for this problem? It's a graph structure. We have developed own graph structure. We built structure of the document. We call it fractal structure, fractal graph, because we can build fractal representation that that behave on different levels of the document. For example, on the level of the sentence, on the level of the chunk of the document, some part of the document, but also we know that Microsoft produce and open source graph rack as implementation of a similar solution to this problem. We have built also this schema that that shows how this structure is built. I will go further. What are different hallucination detection methods? Here we will overview a second part of this challenge, because the first you need to reduce a percentage of the hallucinations in text. But second part, you need to inform a user, operator of the RAG system, that if system produce some misleading, destructive answer, you need to inform a user that it's a bad answer. Don't trust this answer. And there are a lot of methods. Here is attribution method. It have one score, 61%, and this is quite a good percentage of quality. And you can read more about this method in archive paper. Another FactTool, it's FactTool use a variety of tools, including Google Search, Google Scholar, code interpreters, Python. Standard was developed and experiments was conducted with 4 tasks: testing knowledge, generated code, solving mathematical problems, and writing reviews of scientific literature. Our framework use large language model reasoning abilities to evaluate punctuality of content based on the evidence collected. So methodology is fact checking. We need to check facts. Also, another approach here, I would like to emphasize that this approach, fact conflicting hallucination detection, works with various question patterns. You know that there are simple questions exist, but simple we know as direct question. But when we face a multi-hop question, comparison question, ontological question, in these types of questions, LLMs produce hallucinations more frequently than in direct questions, and this framework tackle try to tackle this problem. And here is a benchmark about results of this method, and you can see that Alpaca 13 billion parameters performs ChatGPT in this task. There are also fact tool that tries to understand conflicting evidence. Conflicting evidence can confuse LMs, so can lead to poor decisions. And this method try to find ambiguity in the statement, not common ambiguity. There are approach, and the most common approach is to use cross encoding for hallucination detection. When you have two sentences and you try to understand with when you use sentence transformers with BERT, you produce 1 or 0. Is it hallucination or not
hallucination? For example, man on horse jumps over a crashed plane. Separator. Man on the street on horses. And model response is about 1. And that's a good understanding that it's not hallucination. Our hallucination detection method. We have developed a node method, a pipeline. Take a look at this picture code from GitHub. First, we have an answer that was generated by a large language model. Then we have several documents to support that answer. Third, we break them down into sentences and or snippets. You can break down to sentences, but you have also an option to go further to the larger parts of text, snippets, collection of sentences. For each answer sentence, we can obtain a supporting sentence or snippet in the document. And here you can see that we have two metrics. How do we measure that one sentence have a supporting, a grounding sentence in the document? In our library explain tool, we use cuisine similarity to detect that one sentence supports another sentence from grounding document and generated answer. In the another our library AI framework, author of library is we also developed a Jaccard distance as a metrics. How do we measure a level of supportance, level of confidence that one piece of text support another piece of text. So you can choose any metric you need depending on the of your downstream task. Here is a formula. How do we calculate? We trained a model from BERT, and we estimate the value of the response threshold. So we estimate the proportion of hallucinations as a percentage of the text that does not have support in a supporting document. Here you can see that we produce a length of the supported text from the document, and we also calculate a full length of the generated text. So we divide length of the
supported text to the length of the generated text in answer, and then we substitute this division from 1, and here is our estimation of the percentage of hallucinations, and you can see this implementation of this formula in our code that is freely and open source code is freely available on the GitHub. Another part of the code is where we get supporter snippets. Here is how we produce supporting snippets. You can see here in code that we use some parameter threshold 0.6 as a common threshold for most tasks. But if you are a developer, you can train a model and you can direct, you can put or you can set this probability to your threshold. For example, 0.8, 0.9, and what the task you have, you can use another threshold. And we assessing confidence in answer. We calculate probability of hallucination. If we do not make substitution from 1, then we can get a confidence of the answer. So any end user, any operator of the system that has a RAG subsystem can see this estimation, and the user can decide is it can trust or he's tried to find a mistake if a confidence of the answer below some threshold. For example, as I emphasized earlier, 0.6 or 0.7, depending on your downstream task. And here is examples. I will translate briefly. Three examples. In first example, we have generated text, generated answer, and grounding text. Some text from your business document, your report, for example, and generated answer is not good because no sentence support it in the grounding document. And you can see at the bottom we have an array where we have -1 is that this particular sentence is not supported, and then we have 7, number 7. It means that this sentence have a supporting sentence in the grounding document, and you have an array, and you can calculate a probability of course with normalization. Now, for example, in this particular task, you can see that hallucination has a probability about 90%. It's a bad answer. 90% hallucination, bad answer. We don't trust this answer. In the other examples, we have a better answers, and that has grounding sentences in supporting document. So it's a better answers. So when we implement this hallucination checker in business, in your business unit, in your business product, where you implement it. Here, at the bottom of this image, you can see a rectangle factual assessment model answer. So we put our assessment at the end of the pipeline. So first, of course, we need draft representation, we need a better search of relevant snippets. You need a good large language model that is trained for the iterative augmented generation task. But also, you need a business part when you inform your users that answers good or bad. And we think that this pipeline is right for business implementations. And we compare our approach, and we got about 15 to 18 points lower hallucination level in our answers in retrieval augmented generation pipeline we developed. So we have tested our approach, and it's a really working approach. Here is some example when we see that answer has a link to the grounding document, and users understand that it's a good answer because it has a link to the grounding document. Thank you, and you can ask questions. And Zahar, he's here, and he will kindly answer. Thank you.
Thank you, Victor. Thank you, Zahar. Seattle, if there are any questions from the room or from those who are joining the workshop.
Yes, I do have a question. He's coming right up.
Actually, I have one question. I have specific question. What were specific reasons for using C# for your development environment? It's not often seen for ML projects, in my view.
Я могу ответить на русском? Виктор переведет.
Okay, I will translate.
Я так понимаю, вопрос такой, почему мы используем C#, а не какой-то другой язык. Ну, тут дело в том, что у нас довольно большой проект, в который включает в себя там и тоже логическое мышление, и онтологии, и он изначально разрабатывался на C#. Вот, и поэтому сейчас используется C# для того, чтобы как можно меньше микросервисов создавать. Мы действительно некоторые вещи разворачиваем на Python, но вот C# именно Python используем.
Okay, so the answer is that the project is large enough, and historically it was using lots of ontologies, and these ontologies were developed using C#, and so historically it happens so that everything is done in C#. Any other questions from the room?
Yes,
I have a small question, two small questions. The first question, what difference between hallucination in RAG system and hallucinations in other LLM-based systems, for example, machine translation? This is my first question. And the second question, do you compare your approach to hallucination detection with, for example, uncertainty estimation in LLM for hallucination detection?
Если я правильно понял вопрос, он в чем разница между NAT-детектором галлюцинаций для системы RAG и детектором галлюцинаций обычный для LLM? И
В чем специфика, в
сравнивали.
чем разница между галлюцинациями в задачах RAG и в других задачах, связанных с генерацией? Это первый вопрос, да?
Да.
Второй
Ну,
вопрос про сравнение.
Да, отвечу на первый вопрос. Специфика в том, что в задачах RAG есть опорный текст. И мы можем сравнить то, что сгенерировала нейросеть, с опорным текстом. Вот как раз таки, что там показано была вот эта вот матрица схожести, она и сравнивает по блокам опорный текст со сгенерированным текстом. Далее, когда мы сравнили, мы можем использовать различные методы. Вот о чем говорил Виктор, это расстояние Джакара, и еще использовали, получается, биенкодер на базе SBERT. Вот. Ну и сами обучали биенкодер, чтобы он был как можно меньше, поскольку нужно много сравнений провести. Но вот сейчас мы занимаемся...
Let me translate what has been said. So the primary difference is that when you are using RAG, then you have what is called support text. And if you have a support text, you can take the text generated by the model and you can consider the distance between the support text and the response generated by the model. And based on that distance, you can judge the extent of the hallucinations. Okay, go ahead.
Вот, да, сейчас делаем как раз-таки разработку с кросс-энкодером. Это то, что, наверное, уже ближе ко второму вопросу. Вот сравнение с другими системами. Вот мы как раз-таки кросс-энкодеры добавляем, как в одной из систем, которую показывал Виктор, в нашу систему. Опять-таки боремся за то, чтобы эти кросс-энкодеры были как можно меньше по объему. И далее, вот за счет этой матрицы можно сказать, какой документ в генерации, чем был подкреплен с контекста. И если мы видим, что у нас почти ничего не подкреплено, то мы можем сказать о том, что это была галлюцинация. Ну и вот это почти ничего не подкреплено понятие можно формализовать при помощи гауссовой смеси на базе отклика людей, то есть тот же RLHF, то есть человек может сказать, что была галлюцинация или нет, не была галлюцинация. У нас есть вот это значение, и мы можем его аппроксимировать в плотность вероятности гауссовыми смесями. Ну и в итоге выдавать уже вероятность галлюцинации. Ну вот в этом состоит идея. Если нет опорного текста, то этот подход не работает, поэтому вот здесь именно специфика RAG.
Okay, and the second answer is that they are exploring how to approach this using combination of cross-encoding and using reinforcement learning from human feedback, in short. Any other questions?
Thank you for your answer. And my second question is devoted to comparing uncertainty estimation for hallucination detection and your approach for hallucination detection.
Сравнивали только с таким методом, когда берется текст и вот опорный текст и текст сгенерированный отправляется в ту же LLM и задается вопрос в качестве промпта, если здесь галлюцинация, если есть, то где? Вот. Такое тоже делали, с этого, если честно, начинали. Вот. В итоге нас этот подход не устроил из-за скорости. А по качеству подходы примерно одинаковые, если использовать биенкодер. С использованием кросс-энкодера в качестве метрики схожести рассчитываем, что качество будет даже выше, чем у LLM, если задавать вопрос промптом. То есть, если говорить в цифрах, то у меня на тестах получалось, что порядка 70, вот в 70% случаев правильно работало как наше решение, так и решение на базе LLM, но так как LLM нужно генерировать, сама модель больше и сама генерация идет дольше, то по скорости наше решение оказалось быстрее. По скорости и по необходимым ресурсам, по видеопамяти, например.
Okay, so I think we need to move to our next speaker to get on time. So Anna, Please describe your work, present your work on cognitive distortions detection. Anna, we don't hear you. Please unmute. We still don't hear you.
And now?
Okay, it works.
I'm glad to present my work here. Diagnosis of cognitive distortions in natural language texts. In the modern world, with a high standard of living and unstable global situation, people consume a lot of information every day. Many of these are manipulative texts, what can distort people's perceptions and mental states. The virtual space makes it harder to detect reliable information from false, as we can see facial expressions, gestures, or hear the tone of voice like we do in face-to-face communications. The first example on the slide shows a situation where a fake news tweet saying, "We're excited to announce insulin is free now," caused the stock price of an insulin-producing company to drop for at least a day. The second example is from Facebook, where they manipulated users' news feeds with positive or negative news. They found that people who saw more negative news started posting more negative content themselves, while those who saw more positive news began posting more positive content. In that case, an algorithm that can analyze text and detect cognitive distortions can help. And this algorithm will be discussed further. The term cognitive distortions was first introduced by Aaron Beck, who created cognitive behavior therapy. Cognitive distortions are systematic mistakes in thinking that affect a person's decisions and judgments. Depending on the school of CBT, there are between 10 and 20 cognitive distortions. For example, labeling. When a person makes a mistake, they call themselves a loser or stupid, instead of just seeing it as one mistake. Or catastrophizing. When a person greatly exaggerates their mistakes and their consequences, for example, "I was late for work, now I'll definitely be fired," and downplays their achievements. For example, "Yes, I won the contest, but it's not that important." The main task of this work is to automate finding cognitive distortions to make diagnosing patients and analyzing group communications more objective. The problem with neural network solutions is the lack of large labeled datasets and that these models are hard to interpret. We suggest creating a model for detecting cognitive distortions that is easy to understand and just as accurate as a neural network model. To solve this, we made dictionaries in English with keywords and phrases for each cognitive distortion. Then we adapted the Aigents algorithm created by Kolonin Anton, which was originally used for analyzing text by positive, negative, and contradictive metrics for 13 additional cognitive distortions. An important feature of our algorithm is the use of a scale from 0 to 1 to measure the intensity of these metrics. As shown on the slide, the algorithm differentiates between positive and negative news from the left side and the topic the news belongs to from the right side. Here, this slide shows how our algorithm calculates sentiment and contradiction based on positive and negative metrics. For example, the weather is good, positive 1, negative 0, sentiment, positive plus negative 1, and contradictive, positive multiplied by negative 0. The program breaks down input sentences into n-gram and checks their presence in the corresponding dictionaries. considering the order of the n-gram n as priority. The priority principles work like this. If a tetragram not a bad thing matches, then the bigram bad thing and unigram bad are ignored. Then the algorithm analyzes the intensity of specific cognitive distortions in the text based on the frequency of n-gram found in the corresponding distortion dictionary. The result of the analysis is 16 scores ranging from 0 to 1, showing the intensity of each of the 13 cognitive distortions and 3 additional metrics: positive statements, negative statements, and contradictive statements. After creating the algorithm, we searched for datasets to test its effectiveness. At the time of the search, only 2 datasets in English were available online, and the link to them are shown on the slide. The first dataset includes a passion question column with passion's questions to the therapist, and distorted part column with the part of the question what has a cognitive distortion, and 2 labeled columns, dominant distortion and secondary distortion optional. These columns can contain one of the 10 cognitive distortions described in the study, which is linked at the bottom on the slide. The secondary distortion column can also have a null value. Next, we converted the data into a format what was convenient for us and did a binary classification analysis using our metrics. Since the correlation matrix between columns was quite poor, as shown on the right side of the slide, we decided to compare our results with the labeled data using the F-beta score. For different binary classification thresholds of our results. A poor correlation matrix means there is no linear relationship between the columns, but the F-beta score can help us see non-linear relationship. We look at the F-beta score between our 18 metrics and the dominant distortion column. The best F-beta scores, especially the highest of 0.778 for the F1 score, we achieved at a threshold of 0.5 to or lower for the positive, negative, and contradictive statements. The average metric also did well at the lowest threshold of 0.1. This means that by lowering the threshold, our metrics reduce false positive results, which is important in the medical field. Our result is very close to the 0.79 for the F1 score from the study mentioned on the previous slide. And next, we compared our predicted cognitive distortions with the labeled data. The results showed that our predicted cognitive distortions are almost not related to the labeled ones. You can see this because all 10 tables on the slide are almost completely blue, meaning they are filled with zeros. Some metrics like catastrophizing and disqualifying the positive always had 0 values because they were not present in the dataset we studied. Lowering the F-beta score parameter slightly improved the results, so we did the same analysis with threshold values from 0.01 to 0.09. Lowering the threshold further made our predictions closer to the labeled data, but the values were still very low. The best prediction result for each cognitive distortion in the study we compared to was 0.3 for the F1 score, which is a bit better than our best results, 0.251 for the F0.1 score, and 0.207 for the F1 score. Our best predictions were for mind reading and overgeneralizing distortions. The second dataset has a label column which can take the values distortion or no distortion. Like the first case, we converted the data into a format what was convenient for us and did a binary classification analysis of the text with our metrics. Again, we saw what the correlation matrix on the right side of the slide was not very good. So we decided to use the F-beta score to compare our results with the labeled data. And as shown on the slide, for all F-beta score parameters, the metrics for positive statements, negative statements, contradictive statements, and should statements perform better what other metrics. Like the first dataset, the average metric works well at the lowest threshold of 0.1, because it also includes zero values for cognitive distortions in the text. The F-beta score values improve with lower beta and lower thresholds. The highest values was 0.979 from the left side on the slide. So we have created an interpretable model that can detect cognitive distortions in the text and identify positive, negative, contradictive, and should statements. At the time we made the model, we found only 2 datasets on this topic and none in Russian. So we plan to make our own labeled dataset to adapt our model for Russian in the future. After creating this dataset, we also plan to use machine learning algorithm on it and other available datasets, and then compare the results with our current model. Thanks for your attention.
Thank you, Anna. If there are any questions on this presentation in Seattle or any other pieces of cyberspace, cyberspace?
I think we're all good here. Is there anything else that you have for us? Can you hear me? Hello? Can you hear me?
If there is a question?
Yes.
Okay, did you guys have anything else?
I don't understand.
Did you have any more that you would like to discuss, or we don't have any questions here? So
Okay, yes.
To check.
So if you don't have any questions, then I think we are pretty much done. So thank you, Anna, thank you, Ivan, thank you, Victor, and thanks everyone who attended and who provided the questions and participated in this workshop. So then thank you everyone and have a good day and have a good night.
Thank you. Have a great night.
Bye-bye.
Thank you.
Thank you.
Bye.
Hello, everyone, and welcome to today's session about Nars tutorial. And in this tutorial, it's literally two parts. The first, I will show the big picture and the main about why we want to design this system like this. And the second part, I'm going to show some technical details. But I have to let you know this project is a ongoing project with at least 30 years history. So it's impossible for me to give you everything in this today's tutorial. I just want to remind you on some important parts. Here we go. Okay, but before we start, I think it's helpful for us to show some observations of intelligence. The first kind of observation is called accident handling. And in other words, interruption. And I'm pretty sure most of you guys has been, okay, I'm making it closer, okay. I'm pretty sure many of you guys has been scared of this thing, the fire alarm, right? It will interrupt what you're doing. But before this interruption, let us introduce that you're interrupted, okay. But what you was previously doing was not cancelled completely. You just move your attention a little bit to this new accident and you come back. Therefore, in talking about interruption, we want to mention that this interruption is not about an interruption that means, this interruption does not mean that you have a new task and the new task to complete to take over what you were currently doing and you forgot what you were doing previously. We're talking about interruption in a relatively parallel system to give new situations to draw your attention for a little while. Then you can come back. You can come back, but it's not necessary. We'll introduce it later. The second observation is Pavlov's dog. It's called adaptation or continuous learning. And since usually we know Pavlov's dog will be a dog around a bell and the food, and dog will be really happy about this. It's called conditioning. But after that, I want to introduce two more further experiments of this experiment. It's called extinction. That means if you just ring the bell and you did not show the food completely for a while, the dog will not be happy animal based on the ring. That is because what you have learned will be forgot. Therefore, learning is not one shot, it's a kind of adaptation. Dog adapts to the new situation that, okay, you just have the ring, you don't have the food. After that, we also have another thing which is called second order conditioning. That is previous, okay, dog is happy with the ring and the food. Now you change the ring with the light signal, it also works. So that means that the dog try to learn or adapt to the new situation with the light signal, not the bell, not the ring. The third observation is conservation concepts, the concept level generalization. This terminology, conservation concept, comes from Piaget, talking about, okay, two equal glasses of liquid, and okay, you change the volume to two different glasses. They are equal, and you can also expand this equality from the liquid to equality of weight, heat, numbers, something like this. So from this observation, we want to mention that what you learn, the concept level knowledge, could be generalized to something else. In other words, or to make it more specific, what you learned previously can work on what you were learning now. Okay, let's discuss the first part. To have interpretation, to have this interruption. To talk about interruption, as we mentioned, we want this interruption that draw your attention for a while, and you can quit it if you want. And this system needs to be a parallel system. We don't want, a single thread system. That interruption, that means what you were currently doing completely get turned off. And the time slice in CPU is a very good example for this one. Processes are processed in time units, very tiny time units, processed around 10 milliseconds. And the processes take 0 to many units in a schedule and cycle. 0 is very important, since that means if you have so many processes to be processed, but you just have a limited number of CPU, probably some less important one will be completely dropped. Since not complete drop, that means at least in this scheduling cycle, you don't get a chance. Probably this process will get a chance to be processed every 10 or 100 scheduling cycles, but not in every scheduling cycles. At least they can be processed if we have enough computational resources. Important processes take more time units. This is obvious, right? So if it's important, absolutely you will possess the CPU for a longer time. But this let us know priority is reflected in processing frequencies, not just orders. Here I give you two brief explanations on this part. That is for CPU processing different processes. CPU processing is relatively simple. It does not, the processes might be complicated, but when this process is run by CPU just take a single step to write. It may possess the CPU for a while, but in each single step, it will be a very simple computation. Therefore, CPU tries to give these higher priority tasks with more chances to be processed. That means they are processed more often to guarantee they have the higher priority. This means that we do not need to consider orders anymore. Maybe consider ordering some well, but not too much. We just need to adjust the priority to let these more important tasks possess the CPU for a longer time. Therefore, we can make sure they are processed more. Higher priority processes may take available time slices of low priority tasks. This means, okay, if there are an emergency pop-up, for example, the fire alarm, and it have a very high priority, then in the incoming scheduler cycles of yourself, you're not CPU, but probably process things in a similar way in your scheduler cycle. It possesses it for a while. I mean, in the incoming scheduler cycles, for example, in the incoming few seconds, you may think, oh, it is important to pay attention to pay attention to that. But after that, you think the priority drops greatly. I mean, it does not need you to pay attention to. Therefore, you return to what you were previously doing. Another important thing is that even though the fire alarm draw your attention, you did not forget what you were previously doing. It just means what you were previously doing's priority was decreased, but they are still processed, but in a slower speed. This is so learn from this time slicing CPU. We create system cycles in Nars to build a Nars cycle. And literally we learn from this. We learn from it. We give them different names in the previous in the following talking. Processes are not named as tasks, since Nars is not CPU, but it try to process different things. And now we try to give the terminology tasks to make it specific. And instead of scheduler cycles, we have system cycles. But literally, they point to similar things. To be specific, we have that as a data structure to implement the whole thing. That is an array of groups of tasks. We call them levels with similar priorities. For example, we may have 10 different tasks with priority from 0 to 0.1, and they can be grouped in a level. In processing, we just run, just try to go through all different levels. From the highest level to the lowest level. In each level, we just pick the one task out of the level, for example, pick a task out of the level. It is not empty, and we try to process it. I will introduce later, but I just want to let you know the conclusion that the processing of each single task in our system will also be like the processing of unit, processing of processes in CPU. It will take a constant and a short amount of time. Another important thing to note is that on this slide, I give you 20 different levels, but 10 of them are for tasks with priority larger than 0.66. That means if you have a higher priority, you possess more capacities of this data structure. That means you get more chances to be processed. This is also similar to CPU processing. We give tasks with higher priority, more chances to be processed. As I mentioned, but I just told you the conclusion that processing of each task will take a constant and short amount of time. Except for that, adding a new task will also take a constant and short amount of time. Why? Since it's a new task, you just calculate, you have the priority of that, and you just calculate to which level it should be placed in, and you just put it in, nothing else. So that's popping. That means which makes Nars a real-time system. Why? Because we know which level we are currently working on. You just pick a task out of this level and process it. It is finished. To make a brief summary, in our system, processing of these tasks will take short and a constant amount of time. So does adding a new task. So does picking out a task. Therefore, this will make our system response to new situations pretty quick, since the processing of each single step will take a very short of time. And it is constant, which makes our system a real-time system. Okay, to make a brief summary, interruption in parallel processing is achieved in a high-frequency framework, which requires each single-step processing consumes a constant and short amount of time. And here, I think you might be confused. Since ever since I told you this, you might know this is the reasoning system. Reasoning system talking about thinking. Thinking is different from computing processes for CPU. How could we formalize a thinking process as a step-by-step process? I will show later. Here, we just want to take some notes about this one. Interruption happens in parallel processing that is based on frequency-based priority results adjustment allocation strategy. Next, we want to talk about how to let the system have adaptation. Adaptation is about adaptation of truth values. The truth values is decided by its evidence. That means this is where the name non-axiomatic come from. We want this system to be an open system. That means when you have new evidences, new discoveries, you can simply add it to the system, and the system will consider the old beliefs and the new discoveries, try to combine them. And these things, these new evidences, we will collect these evidences and put it to build up the belief of each judgment. For example, these things, on campus, I see a lot of friendly and big ribbons. Let me use them as an example. We're talking about ribbons are black. And now we have 6 pieces of evidence. One of them is a white ribbon. 4 of them are black ribbons. And we also have a mysterious ribbon that's half black and half white. Why we want to have this last mysterious part? This is I want to let you know the evidence in our system is not simply about a set. I mean, we don't have a set called evidence and you put every single piece of evidence into the set. No, we just account to which amount of this new discovery will contribute to the evidence. We will see the white ribbon contribute 1 unit of evidence, and the black ribbon contribute 1 unit of negative or positive. Sorry, this is positive evidence. White ribbon will provide this, negative evidence. And for the last mysterious bird, it will contribute 0.5 unit of positive evidence, 0.5 unit of negative evidence. Adaptation on the context. This is means, for example, suppose we have 2 islands. The first island will be, as we know, there are more black ribbons. And the second island, it will be a little bit different. It's a mystery island with so many white ribbons. Therefore, when you move from the first island to the second island, your belief of ribbons are black may change. Why? Since you see more and more red ribbons, and these more new evidences will be added to your evidential base. Therefore, you have your belief of ribbons are black will be changed. This also happens on time. Temporal related evidences may expire. I say it is daytime, yes. But after 12 hours, is it daytime? I think the answer will be no. That means the new experience of is it day has dominated your old experiences. We have other examples of adaptation, but here I just want to let you know that adaptation is where the name non-axiomatic come from. We want to make the system an open system that accept new evidences, whether it is a supporting evidence or it is counter examples. They are facts. We have to learn from them. This is a summary, and just repeat what I said. But before talking about the third part, which is about concept level generalization, I think I need to emphasize thinking is not like CPU processing. For this part of things, I just want to, I think I need to convince you guys that thinking process can be formalized as a step-by-step process. We use this logic, non-axiomatic logic, to do this. Harder questions will have more steps, though each step take a short and constant time. That means we have difficulties for different tasks. Absolutely, and they will take different amount of time. But that is for a big picture. If we just take a look of a single step of reasoning, we do not have any differences on the difficulty. This logic is originated from syllogism, expanded while keeping the format. The format will be mainly about 2 parts. The format of well-formed formulas, the format of reasoning. The format of well-formed formula will be, we have 2 terms connected with 1 couplet. For example, ribbon is a kind of bird. And the Raven, the first term, bird is the second term, copula is A. This is how I interpret it, but we have other copulas. Another is the format of reasoning. Syllogism reasoning takes two and only two premises and with one and only one shared midterms. Therefore, they can get the result. From this formatting, we can see if we know the position of the terms and if we know the types of copulas, we can get the conclusion pretty easy. That's why I want to say that in our system processing of each task, we'll almost take we'll take a short and constant amount of time. Since for this single step of reasoning, the complexity, it is really not that complicated. But syllogism is a little bit expressive power is not very it's not very strong. Therefore, we extend the syllogism by adding relations and other things to make it stronger. Relations, this is the grammar. Let me interpret the grammar like this. Water dissolves salt for the first sentence, or we can use a different, or we can translate in a different way. Water and salt, these two things are in a relation. The relation is called dissolve. Another example is Tang have book. Tang is my name, okay, and book. Tang me and the book are in a relation, which is called have. This can be used as predicates, makes the reasoning not only ontological. That means we don't want to talk about whether something is a special type of something or something is a generalization of something. We want to talk about verbs. Except for that, we also include the truth implication. For example, today is Monday. If this is true, then tomorrow is Tuesday. This is true. I know today is not Monday, sorry. With new copulas, extended the syllogism by adding not only categorical judgment. We can talk about judgments about truth value implication. We also include variables, not about instantiation animal. For something is apple, it is fruit. We also have temporal reasoning. Say, if it is windy, then after a while, it is going to be raining. This might not be 100% true, but it's an example. With new copulas, this can be used for causal reasoning. After that, After that, we still have some other features in detail. I think if I have time, I'll introduce a little later. But now I just want to let you know, in our logic, we try to keep the format of the syllogism to which makes the reasoning consume a constant number of time. Therefore, our system use this logic can be used as what we discussed before about the time slicing in the CPU or the system cycle in Nars. By keeping the format, we also extend the non-axiomatic logic to we also extend non-axiomatic logic to expand expressive power, to add more semantic, to add more grammatic rules to that to make it more embedded. Okay, we can then talk about the concept level generalization. The concept level generalization, before that, I think we will start with this short saying. That is, snow is white. It's true. If snow is white, it's by Tarski. Looks like nonsense, but it suggests that semantics should be as it is. Just in the classical symbolism study, we need to interpret the symbol, give them some meanings, give them an interpretation, such that we can talk about their semantics. Without interpretation, they're just placeholders. But here, semantics is not defined by interpretations, but defined by relations with other concepts. Let's start with some examples. For example, ravens are black. In this saying, we are trying to build a relationship between raven, black, and have color. These are three concepts. If we call them concepts, you may call them just a simple perceptions. And the next treaty is raven. This is another piece of knowledge about treaty and raven. The good news is that in these two pieces of knowledge, we have raven. We both have raven the same concept. Therefore, with this same concept at the midterm, we can do some derivations to derive treaty has color black. Why? Since treaty is raven data. This is, we learn from these two pieces of knowledge on maybe from two different reduces, but we can use them together. Why? Since they use the same system of concepts. With this property, assume the perceptor not change. The perceiving of concept is consistent, which will build Nars a large concept network by reasoning. The first sentence means that previously you say this is the bird and after 30 minutes or well, you will also say this is the bird, not something else, right? With this one, we will build Nars, a large concept network that will have a relationship between so many concepts. But we also have a bad news. Since we almost build each perception a concept, it is not flexible as symbols. For symbols, you have ABC as symbols, you can interpret a lot of things. But now we don't have ABC. We just have concepts, and their meanings are decided by the other concepts. You cannot define it just by some definitions. This means we have so many concepts. And the question will be what to process first. To decide this one, we need to introduce the control of Nars. Locate. But before we start the next page, I want to introduce this one additionally. As the previous we talked about the priority of tasks in the system cycle of Nars. But now I want to let you know to facilitate processing in the system, locate a single step reasoning. We locate a single step reasoning with concepts. For example, we have term 1 with midterm at the first sentence and term 2 with the midterm at the second sentence. These two pieces of knowledge is attached to the shared midterm. Therefore, we just need to pick the midterm out, and we know the two premises that can be used for reasoning. Let's just facilitate it. Concept has a budget, indicating the priority, how it's autonomously changed. And this will be introduced. The budget. Budget has 3 dimensions. The first dimension is called priority. That is, the more the concept is precise, the less is priority. It is quite reasonable, right? You don't want, even something is important. While you are processing it, its priority will be decreased since it is going to be finished, right? You do not have to pay attention for it anymore. And this is called priority is the direct evaluation of how important a task or a concept is. Next, we have the second dimension of durability. As mentioned, the more you process it, the less its priority. Durability, that means the decreasing rate of the priority. For the fire alarm I mentioned at the beginning, the durability will be pretty low. That means you pay attention to it just for a while, and after that, you do not pay attention to it. Why? Since you process it and you find, oh, this is nothing important. Its durability is pretty low. Therefore, its priority drops quickly. The third part is quality. That means for some very important tasks, probably you're going to process it for a long while. The quality, that means the minimum value of priority. That means this will not be influenced by the durability. For example, suppose the quality is 0, and this new task will be processed. And the first time processed, the second time processed, the third time processed. Since we don't have a quality for that, in the end, it will be dropped. It will be forgotten by the system. It disappears. But if the quality is not 0, after processing, it will be locked with some priority, and it will be there forever. Given a quality not 0 will kind of make the system a little bit crowded, but that depends. Okay. These are the big pictures of the system. I think it will be helpful to let you know why we want to design the system in this way. What is expected? Now I think we need to spend some time talking about the details about non-axiomatic logic. For this logic, it has 9 layers. Higher layers build on lower layers. That means if I need to introduce a layer 2, I need a layer 1 first. And this is how it is built. And the first layer will be inheritance basics, and I don't want to read all of them since I will introduce them. And except for the last one, the self-control, which is a little bit out of today's schedule. So I will just introduce the first 8 layers. The first layer, I think it's the simplest layer, but it's the most important one. First is about the formats introduced above. So the formats are just about what is called a well-formed formulas, and what is a what is called a well-formed formulas, and what is the formula of reasoning. And we have 3. So let's skip the formulas over here. We'll come to the deduction rule. The deduction rule, the name just shows the transitivities. For example, we have ALV and we have VLC, and we have transitivities. Now, as absolutely, we have ALC, right? This is about deduction. And now, with this deduction as a strong rule, since its transitivity is pretty natural, but how about if we want to guess one premise with another premise and the conclusion? Because here we have 1, 2, and 3. From 1, 2, we get 3. Is it possible for us to, from 2 and 3, we get the premise back? It is possible. We just switch them and rename them if you want to get the induction and get the abduction. The induction tries to, exchange the first premise with a conclusion. Abduction changes the second premise with a conclusion. They're called weak rules since they are not as strong as transitivities. They are just a kind of guess conjecture. Except for that, we also want to introduce a revision rule. Two beliefs may be combined to create a new and a more reliable belief. For example, you have two friends. You have, the first friend told you the weather is good. The second friend told you the weather is good. They are the same. Okay, I know the content are the same, but they from different results. Therefore, for you, you combine these two pieces of knowledge and you get a stronger belief that, the weather is good. As mentioned, Nars methodologic judgments keeps a record of their evidence. So revision is about merging the record of this evidence. Combining all these 4 rules mentioned above, we will have something very interesting. For example, I'd like to know ribbon is black, a black thing. Okay, ribbon is a kind of black thing, no problem. And I'd like to know Tweety with the name of the bird as a kind of ribbon. And you can derive Tweety is black thing, right? Since Tweety is ribbon, ribbon is black thing, and you got Tweety is black thing, no problem. By the way, I want to mention about what's in the brackets. F means a frequency. You may think about the truth value, kind of truth value. Since truth value is 2-dimension, I think introducing the second dimension will make things a little bit more complicated. I just want to talk about the frequency. You just you can think about the frequency in this way. If it is close to 1, it is true. If it is close to 0, it is not true. It is in between. That depends. Okay. This is derived. I mean, from these 2 pieces of knowledge, you guess Tweety is black thing. But remember, this is not a matter system. This can be challenged by new discoveries. I told you, Tweety is not a black thing. It is white. So therefore, I give you a new piece of knowledge. Tweety is not a black thing. This F is 0. That means it's not the case. Okay. Now, what's from this the new evidence, the new knowledge I told you, and with the old knowledge that Tweety is ribbon, you can cause induction and derive a different knowledge, derive a different piece of knowledge that calls ribbon is not a black thing. Okay, and this is as you derived. Then we can try to use the revision rule to revise what you derived from the new knowledge, from the and the knowledge that you already achieved to get a more comprehensive one. To say ribbon is black thing, but it's not. Its truth value is not 1. That means it's not as absolute as before. It's also not 0, since this one is given by a weak rule. It's given by a conjecture. You just try to doubt yourself whether ribbon or whether all the ribbon are black things like this. Therefore, a belief is indirectly updated by the knowledge system. Therefore, for our system, it can use reasoning to try to make its knowledge consistent. But this consistent is just locally. If there are so many knowledge, it is impossible for us to make everything consistent. For the second layer, it's a little bit simple. Since there are so many things, but I just wanted to mention 2 most prominent things: instance and the property. Instances cannot be more specific. For example, Tweety, that's the name of the bird. Can you find any specifications of the name? I don't think so. This is an extreme for things that cannot be more specific. We also have the thing that cannot be more general. This is the property. See the color. That means they can have no generalizations. Third layer will be set theory related. If you refer to the book, you'll find this a little bit complicated. But the critical part in this layer, it will be we will try to use the reasoning rules to create new concepts. For example, probably we're going to create a hot dog from hot and the dog. Remember that maybe at the beginning, the hot dog, when this word is first created, it is related to hot and dog. But I think nowadays, I don't think hot dog is related to hot and dog anymore. It's a new word. That means the concept you created will have its own meaning. It's not dependent on its components. It's not necessarily dependent on its component. It can have its own. For the next layer, we have products and images. Products and images are just the two representations, or what do we call it, relations. Products start with this star or this cross notation. Images start with the spec/location. They are equal. I mean, they refer to the same thing, but with different terms. Let me use this one example. I have the book. Okay, remember, this is still syllogism. The first term will be in this yellow square. It's a long term, but it's still a term. The second term, it will be this is the name of this relation. And I want to try to do some derivation between this knowledge and non-axiomatic logic is a book. Okay, we find it looks like we find the midterm, that is, it's book, right? But no, this is not the case. For the second sentence, we have two terms. First is non-axiomatic logic. The second is book. But for the first one, we don't have book as a standalone book, as a standalone term. Therefore, we'll try to turn this product into an image. That is, book is whatever. This actually means these three sentences refer to the same thing, but they use different terms to represent the same thing. Therefore, by transforming this one into this format, we have book as a standalone midterm. Therefore, we can do reasoning to have non-axiomatic logic is in this kind of thing. And so we translate this image back to product. That means I have non-axiomatic logic, this book. Yes. The next layer will be a higher order reasoning. We know first order logic, it's about our predicate and this and these things. And we have second order for a second order logic. We have predicates about predicates. But in our system, we can explain it this way. Start with an example. Anton said non-axiomatic logic is a book. Anton said something, but this something itself is a sentence. Therefore, we use a statement as a term to make it a second order statement. But absolutely, you can say probably Vincent said, Anthony said, non-axiomatic logic is a book. You got a third order logic. Therefore, in non-axiomatic logic, you can have we just call them higher order reasoning. This is not really special to mention second order or third order. Except for that, since terms can have truth values like that. This term in the yellow square is a term. It can have a truth value. We can have truth value implications. Say apple is a fruit, and then the bird is an animal, like this. I know this is ridiculous, but I just want to give an example to show we can have implications of different terms to have the higher order knowledge. The sixth layer will be variables. Variables is the name in our system is a kind of misleading. Let's consider Kolonin is jam. This one. This is Kolonin and this is jam. And they have evidence from generalizations and specifications. I mean, I can find some specific things to support that Kolonin is jam. For example, Ruby is Kolonin and Ruby is jam. Therefore, and Ruby is the specification of all these two things. Therefore, this one as a standalone example will support the judgment. Kolonin is jam. And we also have something, positive evidence on the generalizations to say we have Kolonin is a kind of manual. And the jam is also kind of manual. Therefore, from as manual as a positive support, we may also say Kolonin is a kind of jam. But in some cases, that means in this case, if you want to talk about Kolonin is jam, you have to consider these two types of different evidences, specifications and generalizations. But in some cases, probably we want to just talk about one side. Therefore, we use variables to separate them. For example, something that is Kolonin and something is jam, that actually means Ruby. Or this Ruby is one instantiation of X. You can find it other type of things. And so this side refers to the specifications. And for this one, symmetrical, it will refers to the generalizations. But absolutely, you can use this variable to as in first order logic to really use it to represent the anonymous entities, or you want to represent to show a kind of relations. Next layer will be temporal reasoning. this temporal reasoning is also a little bit counterintuitive. This is additional concurrence after time-independent reasoning. Let's have an example. There is a chicken. I mean, if there is chicken is true, then we will have there is egg is true. But this does not mention that who is true first, right? Therefore, from this time-independent concurrent, we can have 3 time-dependent concurrent. The first will be chicken first. That means there is a chicken. After that, then there is egg. This means chicken comes first. Okay. The second will be there is a chicken. This is, there is egg. Then there is chicken. Or you can interpret this sentence in a different way. That actually means egg comes first. Otherwise, you can say there is a chicken and there is egg true at the same time. Therefore, you may say, oh, these two things appear at the same time. With only the temporal copula and one term is also a valid well-formed formula considering this layer. That is going to be represent tense. The current time and compare based on the current time, we may use this copula to represent the present tense to say it is Monday. Today is Tuesday. Probably let's consider yesterday. Okay, it is Monday. That means today is Monday. And if you use this one, remember all these 3 sentences are based upon the current time. And this one is it is Tuesday with this copula. That actually means it will be Tuesday tomorrow. And if we use, this should be backslash. If you use backslash, it is Sunday. That means yesterday it is Sunday. Oh, it was Sunday. Something like this. You can use this one to represent the tense to let the system in real time running. That means you just need to put everything in the present tense. If not, you can use other things if necessary in the system to represent what's the current observation. But there is something really strange that the current time changes, right? It is 11 a.m. and you input it yesterday. And yesterday you input this one with the present tense. And if it moved to a current time, to today, it needs to be the past tense, right? Therefore, we use temporal projection based on the timestamp of different judgments to try to fix this. We try to project everything into the current time to do the reasoning, though this will cause the credibility of the concurrent be punished. Next, we go to layer 8, and it will be Go and operation. Since as a real-time system, I obviously mentioned this is a real-time system. This system does not only perceive the environment, it tries to change the environment. Think about this is the robot. The robot runs in the environment and it does not just read the environment. It also tries to do something to explore the environment. This will cause the possible changes to the environment. Therefore, we introduce Go and operation to describe such situations. Go denoted with this exclamation mark, and operation denoted with this arrow. With an up arrow as an up arrow. Go, that is what the system needs to be achieved. You need to turn this goal true. And operation, through executing it, it will be true. For example, I have eat as an operation. It is true if the system really eats something. Go can also be involved in backward reasoning to generate new goals. But usually we call them sub-goals, but this is not a good name, since they generated the new goals are actually independent from the old goals. Here's an example. Exercise will let you be healthy. Sleep well will also let you be healthy. And then now my goal is I want to be healthy. Now you generated 2 sub-goals. First, let's just call them sub-goals. Exercise and sleep well. That means you need to exercise and you need to sleep well. They are generated goals. They are not sub-goals. Why? Since, okay, if be healthy is finally achieved, probably you still want to achieve these 2 goals, but they are independent to the root goal, right? And another example will be at the beginning. Probably I just draw for fun, but now I draw for making money. I still draw, but draw is draw as the generated goal is from this draw for fun, right? And my goal is to have fun. And now this draw is standalone for some other purposes. Another problem about this introduced layer 8 is that may have competing goals. Achieving a goal usually needs operations, and operations may change the environment that makes some other goals harder to achieve. For example, I want to be happy and I want to be healthy. And I have two pieces of knowledge. Okay, the first is if I have a can of soda, it will make me happy. Likely true. And if I have a can of soda, it will not make me healthy. And this is likely false. That means not make me healthy. Okay, but based on the reasoning, I will have two competing goals. And the first is yes, let's have a can of soda. The second goal is let's not have a can of soda. But our system that we consider these two things as two separated goals. They are competing with different desired values. Here I just show a simple case with two related influences. In our system, probably this will be influenced by so many different knowledge. And finally, the goal will be the comprehensive one. That means by synthesizing a lot of analysis of whether I really want to do it, not for just one purpose, but for a lot of purpose, or the purpose in general. That's it. I hope it will be helpful. And after that, Maxim, one of my colleagues, we're going to introduce how the reasoning is implemented in code. Here we go. Oh, we're on break.
It's at 12:45. So I don't know if he wants to start now.
You want to start now, or you want to come back later? Later. I mean, is it okay if we start later? Okay, here we go. You want to come over here?
Yeah.
Okay.
All right, so hopefully everyone can hear and see. My name is Maxim, and I work with Temporal and Owen on the Temporal AGI team. And as previous presentation went over the basics and the high-level overview of where the Nars rules are and how it all kind of relates to each other. And now we're going to dive a little bit into the implementation. And I promise this is not actually super technical, but hopefully by the end of this, you'll see that very simple mechanisms underlie the. Is it good? Oh, sure. Okay. Yes. Sorry, because I need to scroll on this one. Appreciate it. Thank you. Yeah. So hopefully this will be a gentle introduction, and you'll have an understanding of how rules are actually implemented in OpenNARS 4, which Owen will demo later on. So I have a paper out here, and you can check it out for additional details. And there's also a video linked in it. But what I want to focus on at the moment is at the end there's this little graph that pretty much represents at a high level how an inference engine works. So we have these couple of boxes. So over here we have the rules which we just covered. So there's different 9 levels of them, and they're written in a pretty simple format, with 2 premises and a conclusion, along with a truth function that calculates the particular truth value. We also have a parser. Parser is, we use an off-the-shelf parser in our implementation, and it's just a matter of converting strings into usable objects, in this case, Python objects. Then we have the reasoner object, which is pretty much the one that puts it all together. And this is what I will demonstrate today. And as inference, again, at a very high level, what is a rule? And how do we apply it to inputs? So as just earlier demonstrated, it's in a way you can view it as pattern matching. So you have some inputs, and if the inputs match the pattern of the rule, then we can draw valid conclusions. And so the matter is, how do you implement it in a simple way that is easy to follow, easy to maintain, and change in the future? Because something that we can be sure is that things will change. And so this is a Python notebook. You can follow along if you like. It's on my GitHub, so github.com/maxime/NarsWorkshop24. So it's all up there, and you can use it in Colab as well if you like. So one other point is that we're using MiniCanren, which is okay. We're using MiniCanren, which is a relational programming language, and that's the one that actually does the heavy lifting. So I'll go over the details, but yeah, it's just an off-the-shelf library. So going back to the overview of what this actually looks like is, so this is the Python notebook, and you can kind of see that it has the same pieces as this diagram here. We have a parser, we have some rules, and I'll demonstrate those, and we have the inference portion that actually does the matching. So taking a look at dependencies are pretty straightforward. It's just run this first, otherwise things will not work. But the Nars grammar, and as it was demonstrated earlier, so this is the book that the non-axiomatic logic, and it has a formal definition of grammar, right? And it's probably a little hard to see, but there you go. So Nars has a formally defined grammar that we can use to like parse information. And so that's what it looks like in code, right? It's very similar to what it actually, the book describes, because it is a standard format for grammar. And so at the top level, we have tasks. One of the task types is a sentence, if you just follow it like, and then sentence can be a term or a statement with a truth value. In this case, it's called a judgment. And what is a statement? Well, it's just two terms connected by a copula. What's a copula? Copula has these types of, and so it just basically cascades down. In the actual project, the LARC file is a little bit more complicated. And that is why I sort of like pulled it out into a separate notebook so you can follow along, and it only has a few essentials. That way, hopefully, it'll be much easier to understand. It doesn't focus on some of the edge cases that I mentioned, but those are details, not essential to understanding how the system functions. So we have this parser, right? It's just defines the same thing that you can find in the appendix of the book. And so we can look at what the parser module actually does. So this first line here, it just calls the LARC, which is a dependency of this whole system, to just generate a usable file from that grammar definition, just converts it to a Python module, essentially. And so not too complicated, it's just an auto generator, we just call them a tool. And then there's also a parser module, which is basically just maps from whatever the parse tree was created and converts it to Nars statements, which are just, here again, I just pulled out, it's a small subset of what we have in OpenNars, but hopefully small enough that you can wrap your head around it. So just like I said, yeah, there are two types of copulas. Well, there you go. It's just a class that has two copulas with their string representation. And same for, there's a term, can be an atom or a statement. And those are very straightforward. And then those are the truth functions that calculate from the two premises, like how strong is the conclusion that we've reached. So we've defined our grammar, we've parsed it, and now we have this at the bottom of this file. There's a handy dandy parse function that all it does is just takes a string that was passed to it, creates an instance of a parser, and converts it to a term or a sentence. So, and now we can actually call it. And when we call the parse function, give it this string, dog is an animal. I think we can all agree that's true. And it'll create a judgment that's right here that says dog is an animal, and the frequency, so those are the truth values, have frequency and confidence. I don't remember if you covered this already, but so frequency 1, confidence 90, it's default parameters if you haven't provided them, but you can also provide those. And then what's the benefit here? Well, now we can actually extract, so instead of it being string, we can actually extract pieces out of it. And since it's been parsed into a Python object in this case, it exists in many other languages as well. So we can actually pull out a statement, which is the term of the task, and we can get the subjects and copula and predicates individually, and we can refer to them individually at this point. So as you can see, we have a copula, which is the inheritance, and we have the subject dog and predicate animal. So far, we have achieved this first block right here that you can see, right? So we took a string and we created a Python object. So on to the next part, which the reason it requires converting things to logic form, which MiniCanren understands. So to convert from Nars to logic, pretty straightforward as well. This is a cut down version from what we have in the official repository, but pretty much the same stuff, just less details. So to convert from Nars to logic, so this statement right here, how do we convert it to a logic form? Very straightforward. If it's an atom and it's a rule, then we return a variable and a special type of variable, not the Nars variable, but the logic term variable. And then otherwise we return term. If it's a statement, all we're doing is just converting the subject and the predicate to their logic form, just recursively calling the function and extract the copula. Sounds like simple, and it really is. It's just a matter of converting to a different form that the engine that we're going to utilize is going to understand. So really just shuffling some pieces around and presenting them. If you're familiar with maybe some of the languages like Lisp or something like that, right? Like we just create a cons out of it and put a copula first and then subject and the predicate. For more complex things like the relations that Tanguy demonstrated, it's basically the same, just some more manipulation of the pieces to put them in a particular form. And then we need the opposite conversion, because once the engine tells us like, hey, this is the conclusion, well, we want to use it in the Nars form. So we need to convert back from the logic back to Nars. And it's the same thing. As you can see, it's pretty much same type of mapping. If just checking the type of this, if it's term, then it's logic return. If it's a const, then we extract the pieces just like we did when we converted from Nars to logic. Extract the pieces and create a statement at this point. So let me pause for a second here just to kind of give a bigger overview. So this is our inference engine once again, right? So we have the rules. Rules are defined in a very human readable format, and human readable and human editable. So this is just a YAML file, could be a JSON, just a little cleaner, but really same way that you see inference rules defined, for example, in, this is from the book, right? We have a table of various rules, and you can see that it's using the, like, M to P, and given those two statements, M to P and S to M being the shared term, we can derive a conclusion, S to P, using deduction. Ideally, when we're implementing this in a computer system, we would want something that is really close to this type of a representation so that it's easy to go back and forth between them, and so it's easy to maintain for us. And that's pretty much what this allows us to do. So this is the same rule. You can see that it's just a string that says M to P, S to M, S to P, and identifies the rule that is used to create the conclusion. So we have, and this is a small subset, as I said. In the real implementation, there's quite a few more, but same concept applies. So we got this box on the right covered, right, with this YAML file. But we do need to load them up and convert them to logic form, because a string is nice to edit for a human, but the reasoning engine needs to be able to process it in the format that it understands. And all we're doing is really just the same functions that you saw defined above, converting from string to narcisse and narcisse to logic. And that's what this block does. So we took the rules and really just doing some string processing, very straightforward. I think this is, hopefully, if you understand Python, even to the, hello world level, just splitting the string to extract the left and right parts, and then extract the premises, conclusion, and the name of the rule. So very straightforward. And then we call those functions we just defined. We parse, we convert to logic, and then we just return this tuple, I guess, of 4 elements with the premises, conclusion, and the rule. And here are the truth functions. So like that 3-letter name of the rule is actually mapped to a truth function here, which, like I said, it's defined here, but it really, maybe it's easier to understand if you look at, all it's doing is just calculations on the truth functions. So just because different truth functions, some of them are strong inference, some that are weak inference, so it's utilizing that. But as you can see, it's just a map. Like from a name of the function, or from the name of the rule goes to a particular function. That's all there is to it. So we'll load it up and call convert. So that's the function that we just saw here. And that is pretty much what is required to get the rules from a human readable format into something that a computer can now make use of. And here's a little sample of basically like the rules after they've been processed. So this is how they are seen in a YAML file. And then, now we parse them and we actually have those 4 components that I spoke about. We know the name, we know the premise, first and the second premises, and this little tilde, that's identifies a logic variable in MiniCanren. So essentially, we just converted this single string into 4 components and converted those components to logic form. Pretty straightforward. I just print the 3 here. And like I said, you can play around with this. It's on the GitHub. So it looks, it looks like not a lot. And I hope you would agree. And the thing that we are now left with is just this piece right here. So we have the premises. We have a way to convert between strings and narcisse and logic. We have all of this machinery prepared. I guess one of the obvious questions is like, okay, why and what do we do with it? Well, this is where we leverage MiniCanren. And if you expected that opening up this inference box is going to be a very big one, I'm sorry to disappoint you. There's really just a few lines of code here that does all of the reasoning in this case, or all of the rule application. I shouldn't call it reasoning. There's additional steps required for reasoning, but for inference. So we have this function. It accepts the two premises. In this example here, let's just go through it. So given that dog is an animal and Sandy is a dog, Sandy is a pet of mine. And we also know that there is such a rule that in an abstract form says, given M and a P and S and an M, we can derive a conclusion of S and P. What we want is for the inference engine to find a valid substitution, so valid instantiation for these terms here. And if it finds one, to then identify the rule associated with it and perform the substitution to get the conclusion. And that's pretty much this block on the left. So we got the premises. So given that dog is an animal and Sandy is a dog, we convert them to logic form. And then we simply iterate over rules and call this function right here. This line is kind of like the one that pretty much you delete this line, nothing works. You can delete other lines and parts of it will still work. But this is the one that actually calls MiniCanren. And like I said, there's more detail to it, but the way you can kind of read it is, so I want you to find exactly one solution, if it exists, that is valid for the substitution of the conclusion. So conclusion in this case is this, S to P, right, from the rule. That makes sure that MP can be substituted for this and this for this. So essentially it finds the correspondence between the two premises given and the two premises from the rule. And if it can find a valid substitution map, it just performs that substitution on the conclusion and returns the result. It's like this is probably the most complicated one. So everything else was preparation for it, just converting between one type of representation to another. But all of the quote unquote magic is inside of this single line of code. That given this, it will give me a result and it'll produce that, yeah, it is valid to conclude, given the set of rules that you provided, that Sandy's an animal. And the rest is just, like I said, it's just converting the logic form back to Nars and applying the truth functions that we saw by passing the truth values into that, and then returning the result. So as this is pretty much what we see. So we have the two premises by calling the parse function. We call inference, and it will return that it's 81% confident that Sandy's an animal, and it tells us that in order to arrive at that conclusion, it used the deduction rule. Just to have another rule here, to just take a look at it, is that, okay, well, let's try a different rule. And we have Sandy's a dog. Dog is similar to a pet, but here we're like, well, not always, right? Some dogs are not really pets. Some dogs are stray. Some dogs are. And so what we're saying is like, we're like 80% sure that dogs are same as pets. And then based on that information, the inference engine can now go through all of the rules that we've defined and see that, oh yeah, I see that I can apply the analogy rule. And based on the analogy rule, I can determine that Sandy is a pet. However, you'll notice that the conclusion here is less confident because the original truth values were lower and because analogy is a weaker inference than deduction. And so we have, I'm pretty sure that Sandy is a pet based on the information that you gave me. And I believe that is pretty much it. Yeah, like it, like I mentioned, in the real implementation, there is various details, like what you're seeing right now is the actual code for OpenNars 4 that Bowen is going to demonstrate a little bit later. So there's other edge cases and additional things to handle temporal inference, to handle I guess images and implication and products and instances and things like that. But under the hood, if you ever do dive into the code base, I don't want you to be scared, because if you can follow this notebook here, it is the same exact pattern. It's just a matter of converting things to their logic form and feeding it to MiniCanren along with the rules. And MiniCanren just returns and says, okay, this thing fits. And that's it. Thank you. Yeah, any questions or we're good?
Do you just want to do your lunch break now, or do you want to keep going? Yep. Any questions or comments on the Zoom?
Okay, so hello everyone. So my name is Kolonin, and I'm glad to be here to have a brief release of the our new version of OpenNars, which is OpenNars 4. This is a new version implemented in Python, and there are some new features added to the control mechanism of this system. So I'll have a brief introduction to this new version, and I'll show some demos of this system. So you can find this page. So I just released this page to GitHub like yesterday, and this is a tentative link. So we will move this page to the official organization. So you may check this GitHub page in the future, and you'll see the new version of Nars. In this new version, OpenNars 4, the foundations, theoretical foundations remain the same with the old versions, mostly. So you can see we have the same, the same Narcissus grammar. And also the logic part is the same, except that we have a new inference engine. And the major change is about the control mechanism. So, we have a new architecture. Yeah, this architecture is from the old technical report, but it was not implemented successfully before. And we just implement this architecture in this new version. And you can see that we have a memory and inference engine and a internal experience buffer that organizes the system's syncing activity. And also there's an overall experience buffer, which take input from the channels and also from the internal experience. And it organizes the experience from the internal internal activity as well as the outer environment. Channels are the interface between the system and the environment. So the same part is the memory and memory. We have the you can see here the memory of Nars is a conceptual network, and it's implemented based on some data structures, and this part remains the same as the previous version. However, in this new version, we adopt different ways to implement the inference engine, and we add some new features to the control mechanism. So for the moment, we have two alternatives to the inference engine. One is the MiniCanren engine mentioned by Maxine, and another one is an old engine. So we can switch between them. Although in the current code base, the MiniCanren engine, I think it's not fully implemented yet, but we will merge it into the code base in the near future. So so here is the new features in OpenNAS 4. So as I said before, we take this new architecture with multi-channels and two buffers. So we implement a console channel and a user channel, both of which are Nars channels. And I will show you how this multi-channel architecture works later. And also we plan to implement the knowledge-based channel and also a sensory motor channel. So for the knowledge-based channel, like we can connect Nars to a knowledge base like a concept net or a word net, or we can even connect Nars with some LLMs like ChatGPT. And also for the sensory motor channel, it's the interface to perceive the environment. Like we can implement a channel to play the Pong games. So those two channels have not been implemented yet. But those two channels, I can show you the demo later. So and also we implemented for global evaluators to evaluate the overall state of the Nars system. Like you can see, the four evaluators involve satisfaction. It indicates the extent to which the current situation meets the system's desires. And the alertness is the extent to which the system's knowledge is insufficient. Like if you enter into a new environment, then the alertness will be high. And the business is the extent to which the system's time and resources insufficient. For example, you have many tasks on hand, then it will be very busy now. So the business will be high. And well-being is the extent to which the system's body functions as expected. Like if your hands hurts, then the well-being will be low. So we implemented the global evaluators in this new version, and those evaluators are mentioned in the old technical report, but I don't think it was successfully implemented in the old versions of Nars. So yeah, and also a declarative inference engine. Yeah, it's also in progress, I think, but almost finished. Yeah, and so the technical report for this new version is also in progress. And here are some links for the old versions of Nars. Like you can see, this is OpenNAS 3, and also ONA. And this is our team's website. You can see the newest progress of our team. Yeah, so let me show you the demo now. To run OpenNAS 4, you can see the this GitHub repo, and for the moment, I recommend you to just download it, or you can fork it. And yeah, and I assume you are familiar with Python. Oh yeah, and this, yeah, and I assume you are familiar with Python, and you are able to install some requirements. So, and I assume that you have all that prerequisite prepared. So now let's just run it now. You can just like yeah, add a terminal or open a terminal and just run Python Python module, open Nars. And yeah, you can see there's a terminal here. This is, I call it console. And you have two graphical user interface, GUI. And you can, there are 3 channels. So for each window, it corresponds to a channel. Like this is a console channel, and this is a user channel, and that is another user channel. And you can input Narcissus in any of the 3. Like we can input a Narcissus here. Oh, sorry. Like Robin is a bird, which is a classic example. Oh, sorry. Yeah, I have a title here, so it says invalid input. Let me include again. Yeah. So you see, this is the the sentence and with the truth value, and this indicates the channel ID. So the console channel have a channel ID 0. So yeah, and let's input another Narcissus sentence in this channel, like bird is animal. There you can see the different channel ID, which is 1. And let's run like 20 cycles. Yeah, we just input Narcissus in the 3rd channel. And you can see the output is this. Yeah, and so for every, every working cycle, after the cycle is finished, then it will inform the channel that, yeah, I'm finished. Then each channel could get the, can do something like you can do, it can just get the newest derived tasks and print it, and it can be customized. So for the moment, I just let each channel to get the output and just print it. You can see this is the output of the console channel, and this is output of the user channels. And you can see that the derived sentences has no channel ID because it's not it's not directly input from a certain channel, and so it doesn't have a channel ID. And also you will see in the console channel, which is majorly used by administrators, the priority is very high. For example, in this case, it's 0.8. But for the user channel, when the task is input to the system, the initial priorities is relatively low. Yeah, so it's decayed by a certain coefficient. Yeah, so this is basically the the multi-channel functions. And let's just focus on the console channel. We can use Control-C to interrupt. Let's run again. And you can just ignore those. So now let's input something else. For example, we have a goal like now I'm hungry. And then I eat some food. As a result, I will feel good. Now this is a implication or a knowledge telling you like in what cases do what, and then what the result would be. Yeah, and also the goal is to feeling good. And then let's run 20 cycles, or like, no, yeah, that's around 120 cycles. And it derives some goals like, yeah, if I want to feel good, then I should do this. This should be satisfied. If this should be satisfied, then yeah, I should be hungry. And if I tell it I'm hungry now, oh, sorry, it's a typo. And just run again. Oh, what happened? So this, yeah, you know, there's some bugs. Let's run this again. And hungry now. Yeah, so I tell it I'm hungry now. Then it says it derives a goal, which is to eat food, right? So if this is satisfied, then it will derive that I'm feeling good now. So this is you know, temporal inference in Nars, and yeah, and you can try some other examples which can be found here. I guess it's in, yeah. So you can also try the examples in this page. Let me say single-step inference examples, and there are plenty of examples in this page. For example, you can see the examples in L1. This is a Robin swimmer, birdie swimmer, and also you just input it again with a different truth value, then you'll see revision is executed. Let's run this. Let's just restart the window. Sorry. Yeah. And you can give it a different truth value. You see that the default truth value is frequency is 1 and confidence is 0.9. And that's a new belief in which the frequency is 0.1 and confidence is 0.6. Oh, what happened? No error. Yeah, this is a new system, so it's not so stable. Oh yeah, maybe I should fix this. So you can also try some other examples, like for example, this is abduction or induction. Let's try again. And this one is swimmer, this one is bird. Yeah, and now I'm not going to include a certain number which indicates the cycles you want to run. I just want the system to continuous reasoning. Reasoning, I can use control plus R. R is running, and it just run continuously. And you can use control and P to pause. Yeah. Also, you can just try other examples here. So if you make some bugs, you can report it here. Like you can raise some issues, and we'll try our best to fix them. So, and also you can contact us if you have, troubles or questions. You can either use these issues here, or you can contact us by email. yeah, this is our team's website, and I think it's here. Yeah, this is our team members with our contact information, and feel free to contact us if you have questions. And thank you. So, any questions? No. Okay.
Yeah, sure. So this is the tutorial part, and in the afternoon, like it's 2:30 p.m., we will start the workshop part. So let's have a lunch break now.
All of those that are in Zoom, if you want to stay in here, I'll keep the Zoom going. I'm just going to mute.
Nars workshop 2024. And in this afternoon, we have like 7 or 8 speakers. And so for the afternoon's workshop, it is more suitable for the advanced Nars researchers. And we will discuss some more advanced topics of Nars. So the first speaker is Robert Johansson. And so Robert, it's your time. Robert?
Now you can hear me, right?
Oh, yeah. Yes.
Great.
Okay.
And you can see my screen?
Yes.
Yeah. Okay, thanks a lot, and thanks, Bowen, for organizing, and also thanks for adapting to the time schedule. I'm impressed to be able to have participants from, I think, Australia, US, Europe, and also locally. So I will speak about our work on functional equivalence that we have carried out in Stockholm. And I have done this together with Patrick and Tony, that probably many of you know. And this work is funded by Digital Futures. You might recognize the building from last year's AGI conference. And this work really makes use of Open Nars for Applications, ONA, that Patrick and Tony has constructed. So I will say something about our previous work. I will then move to functional equivalence, explain what that is, and then show an experiment that is really typical of the experiments we do, and then some conclusion. And I also really want to recommend this book that is called Psychology of Learning by Jan de Houwer and Sean Hughes. This is a freely available book. It's from MIT Press, but it's freely available online. I can't recommend it enough if you want to understand the psychology of learning, and the subtitle is Functional Cognitive Perspective. So it really emphasizes what is called a functional approach to the psychology of learning. So briefly about our previous work. This is the first thing I will show is actually from it is previous work, but it was accepted very recently in Frontiers in Robotics and AI. I think it will be finally published this week. The title of that paper is Machine Psychology, Integrating Operant Conditioning with a Non-Axiomatic Reasoning System for Advancing Artificial General Intelligence Research. And one example of operant conditioning that we have in this paper is simply something like this. It's a matching to sample experiment that if something like a green color is shown in the middle, it's called the sample, then the participant is taught to choose the blue option rather than the yellow option. And if the red is shown in the sample, the yellow option is trained. So the testing is simply to test what has been previously taught. And using the encoding that we typically use for these experiments now, it can be described like this. So if sample is a location, we describe that as a product between sample and green is an instance of the product location and color. And the match operation is used with the parameters sample and left. So these four contingencies can describe how this operant conditioning task can be solved, and that's described in the paper. It's also possible to illustrate like this, that we typically use these psychological experimental designs, that we have a baseline condition where we don't give any feedback, but when we give feedback, we demonstrate how the system learns it, and then during testing, we don't have any feedback again. And here we track the confidence value of the hypothesis. The paper, one of the papers we presented at the 2022 AGI conference, also in Seattle, right? Was something like this: generalized identity matching. So, for example, with the colors, if the system is taught to choose green when green is the sample and choose blue when blue is the sample, can it then generalize from that to act on the relation between the sample and the comparison? So it, for example, can derive that, if in this situation I should probably pick the red option if red is the sample is red, or pick yellow if the sample is yellow. And this is something that can be represented like this. And the key here is that Nars introduces variables to learn an abstract hypothesis. And once again, it's possible to illustrate like this, that with feedback, Nars learns both a specific hypothesis and a general hypothesis. And during the testing, it needs to use the general hypothesis in the generalized identity matching case. So these two experiments are examples of a research approach where we start at the very bottom. We use a basic form of open Nars for application. This experiment only requires mechanisms from the 7th and 8th layer of Nars. Generalized identity matching requires also abstraction, which is at layer 6. So this experiment requires mechanisms from layers 6 to 8. So what we mean with machine psychology is really an interdisciplinary approach where we combine the theoretical framework of learning psychology with Nars. And one analog is to say that machine psychology is to computer science what psychobiology is to biology. Because we can both manipulate the system's experience as we do in psychology, and we can also choose what mechanisms are available in the system, like what layers are there, so to speak. So we can both manipulate experience and mechanism at the same time. So we typically really, as I said, start with the most basic form of open Nars for application, which can be compiled with semantic inference level set to 0. And using the framework from the psychology of learning, this can be called standard and complex learning. So generalized identity matching is an example of complex learning, and Jan de Hauer calls it effects of meta-regularities. Functional equivalence that I will speak about today is also an instance of complex learning, and it can be called an effect of multiple standard regularities. So functional equivalence. The most basic version to use is if we start up OpenAI for applications like this. And an extremely simple example that if we train the system that in the context of A, I do an operation op1 that leads to G. So the system derives this continuousy. Then 100 time steps later, in the context of B, we do the same operation and followed by G. So the system has been trained in two continuances using the same operation. And this is really what means with functional equivalence, that these A and B are now what's called in the same functional class. So with ONA, if the system acts on both of these continuancy, not only has been trained in them, the system also acts on both continuancies. Then the system derives an equivalence between A and B. And how it's represented in ONA currently is that it's two implications, one A to B and another B to A. But this is really an equivalence statement and A equivalent to B. So once again, this is an effect of multiple standard regularities. If the same operation is used but with different precondition, then an equivalence is derived between the preconditions. And an experiment that demonstrates this. And this is really the, how to say it, it really represents our research approach, that we find an experiment in behavioral psychology and we test that with OpenAI for application. And if Nars can't do it, we try to figure out what is missing. And this is an example of an experiment that ONA could not do until it had the functional equivalence. So in this experiment, this is a paper from 1997. And when I talk about A1, B1, and so on, in the real experiment, it was nonsense symbol. So I think it was children between age 4 and 5 here. So I will use these symbols. And in the experiment, they put these symbols in the middle. And then the task for the child was to move it to one of the corners. So response 1 was to move it in the upper right corner. Response 2 was to move it in the bottom left corner. Response 3 was up there and response 4 was there. So this experiment can then be divided in 3 phases. So during the training, when A was in the middle, the child was trained to put it in upper right corner, which was response 1. So once again, the child didn't work with these symbols A1 and R1. This is an abstract representation. So we will train ONA in when A1 is in the sample, it will do response 1. When B1 is in the sample, it will also do response 1. So it's the same response for A1 and B1. When A2 is in the middle sample, it will do response 2. And when B2 is in the middle, it will also do response 2 with feedback. So this is training. Then the second phase is a retraining, that we will retrain ONA to use other operations with the previous symbols. And then the testing is that, can the system do new operations in a context that it hasn't seen before? So can the system act on a contingency that it hasn't been trained for, so to speak? So it can be the training, the first phase can be represented like this. That if A1 is in the sample, I call the sample S1 in this context, the first board, so to speak. If the system is taught to press R1 both when A1 and B1 are samples, and press R2 when both A2 and B2 are samples, will the system then derive the necessary equivalence between A1 and B1? And with the retraining, the system is with feedback taught to retrain to now press R3 when A1 is the sample. So we represent this with a new board, S2 being a new sample. So A1, then press R3, A2, now press R4. And the testing then, can the system then, when it's shown B1, now press R3, and B2 press R4? So how the experiment can be set up with ONA is like this. We use one press operation with 4 different parameters, and motor babbling set to 20%. And when we present a situation like this, the ONA, A1 is the sample, and we activate G as a goal, G exclamation mark. This will trigger motor babbling if the system doesn't know anything. And since motor babbling R2 in the context of A1 is not what we think is correct, so we will punish ONA by this line. But if in the context of A1 the system presses R1, then we will provide GS feedback, leading to the system deriving this. And we don't do these experiments manually over and over again like this. So we typically use an experimental framework like this, Open Sesame, which is a Python-based framework, so it's very easy to connect to ONA with its Python interface. So the 3 experimental phases are there. And this is the graph illustrating the results that during the training, the system learns the specific hypothesis. During retraining, the system can also learn that. And during testing without feedback, the system can now, in a new situation, use the derived equivalence to complete the testing. And this green line here is the confidence value for the general hypothesis, and the average then of these statements. So it's really the equivalence statements between A1 and B1 and A2 and B2. So during the training, the system gets more, and during this training, when the system gets more and more confidence in the equivalence between A1 and B1 and between A2 and B2. And after it has been trained in that, this thing here, it can use that equivalence statement together with these contingencies to solve this situation. So in conclusion, what we mean with machine psychology, using learning psychology as a theoretical framework, starting with a very small open Nars for application and working upwards from there, it seems like a fruitful approach. And we have started with operant conditioning, that is in this framework called the effects of standard regularities. Our previous work, generalized identity matching, is an instance of complex learning. Functional equivalence is another example then of complex learning. And it really seems like an important mechanism to add. It makes ONA more adaptive, so to speak. And this is already available in ONA, in master branch. It's already checked in. I think Patrick extremely recently changed, so you have to, in the config file, set functional equivalence equals true or something like that. But anyway, it's part of the master branch. So thank you very much. And any questions?
So do you have any questions? Yes. Okay. Mhm.
Hey, Robert.
Hello.
So I have a question. How does it relate, in your view, to the concept of cause-effect relations? And can you say something more about sort of how it relates to maybe other, let's say, reasoning mechanisms? Yeah, we'll stop there.
Mm-hmm. So I know that you have a strong interest in causality and that you do a lot of, and your students do a lot of exciting work. And I can only speak from my own perspective on that, so to speak. And from that perspective, I would say that to start with, I think it's very important to make a distinction between what the researcher thinks when he or she talks about causality and how the system experiences causality. So if we only speak about the system, I think this simple operant conditioning is an example of causality. The system learns some kind of, if this, then do that, and that leads to that. So that's the most basic form of causality in a sense. And since it's called effect of multiple standard regularities, it is, I think, really one step up in complexity when it comes to causality, because it's really like this is some kind of causality between if A, then op1 leads to G, if B, op1 leads to G, combining these causes this to happen. So it's really one step up in complexity in that sense. And the final thing is that the kind of causality that I think you really are talking about is what I would call the verbal form of causality. That when we learn something that, for example, if a random thing is before another random thing, then we can derive things regarding that the other is after the first and so on. So it's really more kind of the things that animal can't do. And that is what I would say beyond what I have shown today. That requires language in a sense.
So, yeah, thanks. So, yeah, this is really close to my heart, and I think you're doing really great work. My mind wanders automatically to the zooms out and thinks, because I think a huge difference between our machines right now and the human mind is context. So the human mind can travel on various levels of detail, and our machine experiments tend to be really narrow. So one of the conundrums here in my mind is how people select between what matters and what doesn't matter when they make these kinds of inferences. Is there, for instance, a threshold between what some child, 5-year-old or 8-year-old or 15-year-old, whatever, considers as being equivalent? Functional equivalence, in this context, would seem to be a lot more complex than the experiments. That's not a criticism of your work, but rather an observation of where we might want to go here. But if I were to summarize my thoughts right now, it's, the question of context in the human mind, and also relates to the artificial situation of a child in a psychologist's office, which has often been criticized because, people probably don't really behave the same way when they're sitting at a desk and they know they're doing a task, and they somehow, are more nervous, and, it wouldn't maybe reflect necessarily exactly how they would do this otherwise. But of course, ultimately, what we want to know is how these kinds of rules that are automatically created and managed and represented in some way in the human mind, how they are used in context and how they relate to other such things, and how long do these rules live in the human mind versus the machine. So yeah, I guess that's just rambling, and I don't have a question unless you want to unless you have some thoughts on that. I'll stop here.
Yeah, thanks a lot. Yeah, I think we're in total agreement. So as you might have detected, that my primary interest is what I typically call the arbitrarily applicable relational responding. You and me actually talked about it in 2019 in the Shenzhen conference. So that's the behavioral psychology way to talk about verbal behavior, and the kind of causality that you really talk about, that you also highlight, that I think is great, is very much contextually controlled. That is really an instance then of arbitrarily applicable relational responding, which is one step up in complexity from what I showed here. And we really have some clues, good clues, I would say, on how to represent that with Nars. And I think personally the most exciting things that would be in addition to what I've shown today is to use NAL4 relations, acquired relations. So for example, the system having a very simple animal level learning, like if A is presented and then B, of course it will be a simple prediction from A to B, but the system might also acquire a relation, that there is a relation here. And that is part of the verbal behavior then of it can then be called A is after B, using the acquired relations. So I think personally the acquired relations is really what enables this more advanced verbal behavior. So I hope we can talk more about that later.
Yeah. And let me abuse my position here at the podium before I sit down and ask you if we could maybe set up a meeting where we talk about this some more, because I'm preparing an EU grant proposal, and I think this would be a fantastic addition to that. I hope you're open to some thoughts, some ideas and discussions on that.
Wonderful. Great. Thanks a lot, everyone. Have a nice rest of the workshop.
Okay, thank you, Robert.
Thank you, Bo.
So any other questions? If no, then we'll move to the next talk. So, let me share the screen. My name is Bowen Zhu, and today I'll share my recent works. They're about sequence learning and sensory motor learning based on NEL. NEL means non-axiomatic logic, which is the logic part of Nars. I started this work like about 2 years ago, and I started the work from sequence learning. The sequence learning refers to acquiring the proper ordering of events or stimuli. So in Nars, we use temporal inductions to learn some, the order of events. There are some preliminary mechanism in Nars to learn some sequence patterns. In this work, I researched some more advanced techniques, and I built a new model of conceptual networks which can do sequence learning. So in my view, sequence learning procedures should be online and lifelong. So in the traditional methods like neural networks, for example, LLMs, for example, transformers, LSTMs, RNNs, and so on, some of them can do online and lifelong learning, but some cannot. So my aim is to construct a model that can, do online and lifelong learning. So in this research, I define the problem as below. So give us a sequence of events, like you have A, B, C, D, and some random events, and then X, B, C, Y. Each character, like A, B, C, D, means a certain event. And here the dollar mark means a random event. It can be, any concept. So given this kind of sequence, the problem is to predict the next event which will occur. And so in this example, BCD and BCY, those two pieces of the sequence are predictable, while $2 dollar and A and dollar X are non-predictable. So in this example, the theoretical accuracy is around 50%. And more generally, the input form is like this. I guess you can see my cursor. There are some random events followed by some deterministic events. So most of the deterministic events are predictable, so that you can generate data sets in this form. And the meta goal of the system is to predict the next event given this kind of sequence. So to give you an intuition, let's consider the following two sentences. The first one is, to save money, I go to the bank every month. And the second one is, on the bank of the river, locate a restaurant. So you can see the words bank here in the two sentences have different meaning, right? So the word bank corresponds to a concept bank. Under different sequence contexts, the different parts meaning are exploited. So to handle this ambiguity, we need a model of sequence learning. To build such a model, I refer to two kinds of works. One is a brain-inspired work, which is HTM. It's a famous work in the AGI field. So I adopt a mini column structure, and the column roughly corresponds to a concept. Well, a node inside the column corresponds to a concept, concept under a sequence context. Just remember the bank example. The concept bank in different sequences have different meanings, right? So this is why I adopt this kind of structure. And the second source of this work is Nars, and more accurately, it's NAL, non-axiomatic logic. And a link in this model, like A linked to B, is interpreted as a sequential equivalence. Like A temporarily, A implies B with a order, and a chain in this conceptual network, like A to B to C, is interpreted as a sequential equivalence with a sequence as an antecedent statement. Like this kind of statement, A and B implies, it's a typo. A and B implies C. So so through the logic, this kind of model is fully interpretable and explainable. And I hope this kind of model can be, can do online and lifelong learning. To achieve this, the links are created and deleted dynamically in real time. The same with the concepts. The concepts can also be constructed dynamically. And for the to understand this model, I would say 2 points. The first one is the network is analogous to a filter in the exploitation procedure. Just suppose that we have learned a network with some nodes and links, and how to use that network to predict future events. Then I would say it's a kind of filter. Multiple possibilities are considered simultaneously if no anticipation occurs. Well, if there's some anticipation, and anticipations are generated according to existing knowledge. For example, suppose you have learned some implications from the past experience, then even the current event, you will predict what will occur next. And that is an anticipation. And those anticipations are generated online or dynamically. And if events with wrong anticipations are filled out, if it's a wrong anticipation, then we do not consider this further. However, if it's a correct anticipation, then it will be the corresponding concept or contextual concept will be activated, so that it will remain in the like working memory, or it will remain active. So the wrong events with wrong anticipation are filled out. This is how this model can predict events with different sequence contexts. And so for the learning part, in each learning step, there are 3 sub-steps. So the first step is to hypothesize, which means it creates some new links or statements in L with low initial confidence. And the second step is to revise, which means using temporal induction and revision rules in L. And the third step is to recycle, which means dropping out some links with low priority and quality. So through this kind of mechanism, this network can do online learning. So this is a demo video. You can see the concepts. The links are dynamically constructed as time goes by, and the prediction accuracy is increasing. And this conceptual network become more and more complex. And let's see the final result. It's a very complex network, and accuracy is around 50%. Okay. So there are some more interesting results. I did an experiment about continual learning. Say in different period, we let the system to learn different groups of data sets, and then change to the next group and next group. And after several groups, we just come back to the first group, and we want to see whether the system still remember the previous knowledge. And the result is that the system remember the previous knowledge and can do even better. So my conclusion is that the network doesn't suffer from catastrophic forgetting, which is a very big issue in neural networks. So the accuracy in some parts exceeds 50%. So I was confused about this, but now my conjecture is that it learns some patterns from random events. And I also compared this network to some traditional models like transformer and LSTM. And you can see the orange line is my work, and the green line corresponds to transformer, and the blue line corresponds to LSTM. And we found that in online learning problem, this model performs similar to transformer, while they both perform better than LSTM. So here are some implications. Yeah, if we view this kind of network as a program, then I found that it can do such a sequential execution, just execute operations step by step, or it can do if-else branch. Like if there is a sub network like this, it corresponds to a program on the right-hand side, or it can also do a loop. We just have a link back to the previous node, and it corresponds to this kind of program. So I found this kind of model can execute a certain programs, or it can learn some programs from experience. And also I found that the model performs the continual learning ability without catastrophic forgetting. This is easy to understand because this model adopts a concept-centered representation, so that that annoying issue should not occur in theory. But note that the system is still able to forget due to insufficient memory resource. Okay, there are also some limitations in this work. The first one is that the current model assumes that only one event occurs at each time step, but this may not be true in some more general cases. And the second is that it doesn't learn a hierarchy. Hierarchy exists extensively in human cognition. So the issue is how to learn a hierarchy in a conceptual network. That's I think it's an interesting question. And the third one is that a mathematical proof of the learning mechanism is lacked. So I tried, but I failed. And also this is is left for the future work. If you are interested in this work, you can find the source code and also the newest manuscript on GitHub, or there's a preprint version, but that is an old version. And I recommend this newest manuscript, which is more clear, is clearer than the previous version. And I think this is done by last year. And this is a more recent work of sensory motor learning. In my view, sequence learning is the foundation of sensory motor learning, because to perceive a picture, you can convert this problem into learning a sequence, and I'll explain how. So this is my motivation. I asked a question a few years ago: how does Nars know Robin is her? This is kind of it seems a very simple question. How does Nars know? You just tell it. you can just input the Nars to the system, right? However, does Nars really understand what is robin, what is bird? Does it really know that robin is bird? Well, we can say it knows this kind of belief to some extent, because in Nars, it adopts experience grounded semantics. So we can say Nars understand the meaning of robin in a sense that robin is a bird, but the Nars system cannot connect this concept to a concrete image. So in human beings, we firstly see different instances of birds, and we found that those groups of birds have some similarities, and another group of birds are different from this group. And then we categorize them into different birds, and then we found that they have some general features, so we call all of them as birds. This is the natural path of perceiving something which is called a bird. Yeah, that's more complex than just telling it a narcissist. And in addition, in most cases, we do not see the whole image. Like if you just see a bird, then you can see the whole bird at one glance. However, in many cases, we just see part of it. Just suppose the universe, you can perceive the whole universe at once, right? So we just perceive different parts of a universe and construct all the parts into wholes. So that just let me, that guided me to think about eye movements. You can see the picture on the right-hand side. Maybe I can make it. Yeah, this picture. You just scan through the whole image, the whole perceptual field, and you see different places. You just fixate different places, and then construct the whole from many parts. And maybe I guess if this is a general principle, then in lower levels, maybe it just do the same thing. It like in the lower when we just recognize a small feature, we also use some principles similar to eye movements to perceive this feature. Yeah, this is just a hypothesis, and yeah, this work is far from mature, and I have more questions than answers. So I think in this topic, the key question is how should an intelligent system perceive the world? So I use the word should because I think we need a normative theory. Then in this normative theory, what properties do we want? I just list some of them, but not all of them, because I think this is not a comprehensive list. So first of all, I think perception involves both sensing and acting. So it's not just observe the world passively. It's just not do observations. Rather, it perceive the world actively. It actively moves its perceptual field, moves its attention to different parts of the world, and construct a whole from different parts. And the second point is that an intelligent system should move its perceptual field, constructing wholes from local observations. The third point is that the perception procedure is an endless loop. I think it's very different from David Marr's theory and traditional works of computer vision, because in traditional computer vision, it's an algorithm, and the system just extracts features and categorize them, or do some similar thing and stop. However, for human beings, it's a different story. given few time, the system gets a rough impression of a scene. However, given more time, the system fetches more increasing details. Yeah, if we are in a hurry, then we just have a just have a look and say, oh, where's the? Maybe we can just recognize one or two objects, one of two novel or most important objects. However, if we have enough time, then we can remember more details about this scene. We can see how many people are there, or what is on the table, and so on. And maybe there are some more properties of such a system, and then given these goals, how to build a theory or how to build a model to do sensory motor learning. I think if we use the current non-axiomatic logic, then to represent an object, we can use conjunctions. Like if an object has 7 parts, like 7 features, then of course you can use a conjunction of those features. Like I denote them as C1 through C7. But the problem here is generalization. If you just if one feature is lost, then the truth value of this object is very low. But for human beings, lacking some observations does not matter, right? So we have to use multiple conjunctions, like you have C1 through C6 without C7, and C1 through C5, and also C8 without C6, and so on. So by using those, I think it's 8 conjunctions, we can represent this object. And this is, of course, too complex or too, troubling, I think. So the question, is, can we design a simplified and efficient representation? So in this project report, you can see this. This is done a few months ago in an AGI course provided by Palantir, and I touched the topic of sensory motor learning, and I formalized the, I just provide some formalization, and I wanted to extend the representation of Nars. Although this is a preliminary work and it's immature. For example, we have in this here you see W means whole, and this whole is composed of n parts, n components, C1 through Cn, and each component has a relative location, and and this is also called a prototype. And a component, if a component occurs in a certain location, then this contributes to the truth value of this conjunction compound, to this compound. So based on that view, I write some code and do the experiment, and you can see, the setting is that there are 3 features on the, there are 3 features in this world, and at each time step, the system can just perceive a local part, like it just can perceive this feature, and the system needs to decide where to see next. And according to its knowledge, it will move left, and because it predicts that on the left there will be another feature, and if it sees that there is indeed a feature there, then it's more confident. Then it will do next prediction and move to the next place. And here, the match value just means the number of the amount of evidence. Yeah, and this is also a endless loop. The system initially have a very low confidence, but with time goes by, its confidence just increase. So you can get the code and this video in here. Yeah, here's the the report, the code, and yeah, the code and the video are compressed in this file. Yeah, so yeah, that's all. That's all my presentation. So do you have any questions? Yeah, and in that report, for the sensor motor learning part, I didn't provide many details, but you can find some details here. Like I defined a new, like, although when I discussed with Pei, he said he don't like this, but this is my best solution for the moment. So I still want to share this. I defined a new controller and also, a new compound connector to represent a prototype and some inference rules and how to compute the similarity of location and so on. Yeah.
So how is the system doing predictions?
Do you mean which work? Sensory motor learning or sequence learning? Okay. So I think it's the same thing with sequence learning. It has a knowledge which is represented by Narcissus, and if it see a certain feature, then the corresponding compound is activated, and then it predicts the other components of that compound according to a certain inference rules. So the then by this some anticipations are generated, and then the corresponding concepts, their priority will be higher, and through a decision-making procedure, it just pick out a concept with the highest priority, and then move to check whether that concept is true.
And how is the priority computed?
Oh yeah, so it's similar. Oh yeah, so if the anticipation is correct, then just make it higher. Otherwise, it's wrong, then make it lower. So if the system is right, then the corresponding concepts will be the priority will be higher and higher. Yeah. Sorry, say again. So because we don't have unlimited memory. No, it's limited. It's still limited. Yeah, still limited. It's insufficient. No, it's limited, but if there are many few prototypes in the memory, then it's relatively sufficient. But with time goes by, prototypes are more and more, and then it will forget something. Okay, thank you for questions. So if no more questions, then we can move to the next talk. If time really. Okay. It's your turn.
Okay, good afternoon, everyone. And today my topic, I'll be talking about temporal reasoning. This is the short topic, but I would like to cover 3 subtopics. I'm really from Temple University, AGI team, and let's start. Before we talk about some technical details, I would like to talk about some observation from sports about this temporal reasoning, why we need this. And think about your play against your opponent, and absolutely. You need to put an eye on your opponent's movement and wisely pick your strategy and give a counter attack. This and so I mean all above things happens in very short period of time. Therefore, we need this temporal reasoning to be a high-speed adaptation, a wise adaptation, since our opponent's strategy may change, and your opponents may take some variance of the variance of the moment. With very small variations, but literally the same. Think about shaking hands of 2 different guys. They're just shaking hands, but the actors involved in this behavior might be different. The last one will be dense combinations. Since this temporal reasoning will be about, well, let's just recall what happened currently, and we have the history. I mean, a line of different effects, and we want to generate a pattern from them. Therefore, the combinatorial problem will be a very dense problem. Let's talk about the path to achieve them. This is the first part, which is the frame of temporal pattern recognition. Matching between different temporal patterns and matching with continuous values will be the separate topic. Let's start with the first one. This is mainly achieved by an architecture called image buffer. If you know Nars 4.0, I think this function is already there. This is the framework for temporal pattern generation. We need to first record events, like I mentioned. We need to recall what is happening now, and this now is moving forward. And the generalized compound, like I mentioned, you can recall a lot of things, but probably we don't want to use all of them. We want to use some of them, but to which part we want to use, that's a problem. Generate implications. That is, we want to use it, like I mentioned before, a quick adaptation that we want to use the temporal pattern to do something. And this make prediction is about our purpose. Otherwise, there are so many things to put an eye on. It's impossible for the system to distribute its computation without this specific attention. Image buffer. Let me introduce structure a little bit and tell you how this patterns, how this compounds are generated, implications are generated, prediction are generated and verified. The structure, the first part will be called slopes. It only recalls events, recalls observations. Here we go. And a float will be like this. You may load an event to it, the second event to it. You may load a lot of events to it. And and we have a slot for each time moment. In the middle, we call it the current time. That is, what is currently happening? I want to write something down. And we also have some previous moments, just -2, -1 moments, just the previous one. For example, if I take the time window of 1 second for each time slot, the current time just means in the previous 1 second, what was happening? The -1 just in the previous 1 to previous 2 seconds, what was happening? You can keep records of such a thing. For the future, this is different. It's impossible for us to really record some events for the future, but we can make predictions. For example, looks like I'm going to be cloudy today. Therefore, I may write in the future slots to say, oh, it's going to be cloudy. For the anticipation parts, this will be mentioned later. Just like this is closer related to the events, the future moments. But before we talk about the prediction, I don't think introducing anticipation is a good choice. Rotation, the capacity of an event buffer is limited. For example, if I have a note, I just 10 pages, but that's a short notes, but let's just take 10 pages as an example. And that just means I would like to keep a record of the most recent 10 time slots. But time's going on. When there is a new moment comes in, that is the oldest moment will be dropped, like this. We create this new time slot D and add it to the window and drop the oldest time slot A, and we keep the size of the overall structure. Reaction table. That's also called the prediction table. That is where the anticipations is from. Anticipation and the predictions are different. We'll talk later. For example, And over here, from this history, let's just put an eye on this -2, -1, and 0 time slot. We record event 3, 4, 5, 6, and 1, 2. We probably want to give some predictions based on the history. That is, after E3, there is E4. That is, we have event 3, and after that, 1 moment later, we have E4. Therefore, we may create this prediction on E3, next E4. We can also create E3. We just have an interval for 1 moment, and after that we will have E1. Therefore, we write this E3 plus 1, E1, and you can create other temporal prediction like that. But these are just examples. How to create them? We need to, there are so many of them. The detail will be introduced in talking about attention. Let's just assume some of this prediction can be generated in this way. Interval is not in narcissist. It is referred when anticipation is generated. And this is, for you guys not familiar with narcissist, the might be a problem, but you may think that this E1. This E1 is not recorded in the representation of this language. We'll just say E3. After E3, there will be E1. But this plus 1 will tell me that, okay, it is after 1 into, I will put this one. With these reactions, with these reactions or predictions, we may generate anticipations. The name reaction is from that I deliberately create this part as a production system. That is, when some preconditions are satisfied, the result will be directly created and as an anticipation put in a corresponding time, corresponding moment. For example, if the current moment we have event 3. And we have an anticipation or prediction. This is called we have a reaction or prediction called E3, then E4. Then we will create E4 as an anticipation in the plus 1 moment. And E3 plus 1, E2, that means we're going to create E1 as anticipation in plus 2 moment. These are how the anticipation are generated. Anticipations is really important things. It will help us to focus. And is also, I think it's also the only way for us to give some counter examples of the predictions. Since predictions can be generated based on history, it's okay. But how do we find out that the prediction is actually wrong? That is it? I don't think it's a good way to think, okay, I cannot generate this prediction anymore, it's wrong. No, that is because with this prediction and I want to use it, but I did not get the expected result. This is wrong. Therefore, by generating anticipations, when the future moment becomes a current moment, I may check the anticipations. Whether my anticipations are there. If not, I'm going to punish the corresponding predictions to give them counter examples. Okay, and since there are so many of them as a priority queue, the capacity is limited. Low quality reaction is not used, but keep the things. For example, we have so many of such reactions, but we just want to keep the top, some of them, in the production system. The remaining part might be called not very good, but we want to keep them the right things. For these active reactions, they may accumulate with counter examples. Then the priority get decreased. Then we get some space for the inactive reactions to be active again. And this large space also will provide a buffer for generating different reactions. And anticipation checked when the future moment becomes the present moment, like I mentioned. If, for example, we have these purple blocks as anticipations, we have 2 anticipations in the present moment, E10 and E1. Now we have the E1 to E1, and this is matched with my anticipation. Okay, the matched anticipation and the award and punished can be given to the reaction. Then also another name, the prediction used based on the truth value. If I'm going to expect it's going to rain, okay, it actually does not go to rain. It's sunny day. Therefore, that means it is still matched, but this match means my anticipation is wrong. This will cause a punishment for the prediction. Or field anticipation, just like this E10, we don't have any match situations, then it's going to get punished directly. Another part of this one is called agenda. Since I mentioned Nars is a system designed for a real-time system, we don't want the system to be simply an observer of the system. Now, observer of the environment, it may needs to execute some operations to really change it. Therefore, when I'm going to do the operations, this is recorded on the agenda. Agenda is not attached in the slopes, because we may have a situation like E3 plus 1, then E1, and E1 plus 1, then E2. By combining these two things, we may have E3 plus 4. That is then E12, like this. This one view, we can see that this interval already exceeds the time span or the capacity of the slopes, but it is possible by reasoning. Therefore, in this case, if we want to do some operations in this situation, we can only say, okay, after four time slopes, after 4 time moments, I need to do something. But it's outside of the capacity of this one, we can only record it on the agenda. Let's see, when the time comes here, I need to do something. Next, we want to talk about this component generation. Since previously we mentioned about the structures, then let me introduce how the structures are fused and generate something. Component is generated based on the most prominent one. If we first define the most prominent one, what is called the most prominent one? There are 3 things we need to check. The first is by anticipations. See, anticipation, that is my previous attention. I would like to check something in the future. Therefore, I need to check whether it is about my anticipation. If not, I think it is not as what I expected. Its priority will be a little bit lower, but we need still have 2 other evaluations to increase its priority. Next is signal magnificence. Think about some very loud noise. It will definitely draw attention, right? Since its signal strength is real strong. Next is the priority of the priority in the memory if it existed. That means this buffer is outside of Nars memory. If we want to mention something, it is better for us to check whether it is already of high priority in the system, or on the other hand, whether it is of a low priority. See, the system currently does not want to think about this. By considering these 3 factors, we may give these atomic observations a priority value to pick out the most prominent one. Think about it. In this one, we have the most prominent one as E4. Then we do enumerations to generate this, what we call the concurrent compounds. Say E4 and E5, E4 and E6, E4, E5, E6. I know you don't like the word enumeration. Sure, I also don't like it. But look, sorry, this is the only way in talking about this in this buffer. Since in this buffer, this is extremely unpredictable. We don't know which compound will be useful, which compound will not be useful. Therefore, we try to limit the size of the buffer to cannot limit the size of enumeration. This could be finished by first, we have a very small or tiny time window to say, oh, previously we may have 1 second for each moment. Now we have 10 milliseconds for each slot. Therefore, the events recorded in each moment will be relatively small, and the combinatorial problem will be cannot solved. But I want to let you know that the design here is to do enumeration, and to make it quick, we have to involve as few events as possible. This could be done, but this will not harm the system. We just need to narrow down the capacity, or we just need to narrow down the time span of each moment, and this will happen. But there are some drawbacks. We'll mention later. Abundant of absolutely. Prediction table, agenda, reactions. It will create such thing. Oh, sorry. oh, sorry. In this which something is wrong with the slide. Let me talk about this. Sorry. Sorry. Let me continue with this page. This is called concurrent time. This is called concurrent compound generation. Since we generate the compounds inside the time slot, but after that we generate compounds inside the time slot. We can also use the generated compound by combining with the compounds generated in previous moments. Therefore, to trigger, for example, previous moments next with the current moment to generate a successive time compounds. That is much like a pattern of the systems of the system perception, and generation of predictions are also the same. We take the previously most prominent one combined with the currently prominent one to generate the predictions. Next, this is this is the basic idea of event buffers. We try to give a time window and record the events then generate compounds by enumeration, and combined with the prediction, the signal significance, and Nars memories help to filter out some high priority ones. That is one we need to pay attention to. And but we still have some questions since there are so many variants. Let's give an example of handshake. In this one, I want to emphasize that we talk about the same behavior, but with different entities. To recognize this is the same behavior, reasoning is needed. And for example, I shake hands with Anton and Liam shake hands with Vincent. We are, the two groups of guys, we are shaking hands, the same behavior, but how do we identify? We are shaking hands, we are performing the same behavior. This can be done by reasoning to say, oh, I am person one, Anton is person two. And this is a behavior between person one and person two. And the second is also Liam is person one, and Vincent is person two. And by reasoning, we can get the same result to say, oh, they are identical. But the question is that this is, remember, in this buffer, this is about high-speed adaptation. Therefore, it's possible that we don't have enough time to request Nars to give us some system cycles to figure out this reasoning result. Therefore, we need to find some shortcuts to finish it. To be more specific, I mean to let this one fit with our discussion. Probably we have E3. After that, we have E4. And E3 after that, we have E5. Probably we want to say these two. I mean, the human being probably want to say these two patterns, these two compounds are similar under some semantics. How do we figure out? And therefore, I created a shortcut method called gradient descent pattern matching. I use vector symbolic architecture, offers way to this one offers a way to formal representations to vectors. Therefore, this E3 plus 1 E4, this conceptual formal representation can be turned into a fixed set vector, so that the lower one. And as a result, compounds can be represented as vectors, like I mentioned before. If the entity can be flexible and matched, like different individuals in handshake, we need to define it in advance. Say, if we assume that E4 and E5 can be changed, this means that E3 want to do something with the next, or we don't care about what the next is. Then we just need to train the vectors of these flexibly matchable vectors, and we can identify whether these two patterns can be matchable. I used this one in a graph isomorphism matching. With the vertices around with the number of vertices around 50 and number of edges around 200, the match result will be pretty good. And by the way, although I use the gradient descent technology over here, it is not related to neural networks. Okay, I just want to use gradient to train something. That's all. So this is the try to solve the first kind of question that is called abundant variance. So many abundant variance, but with small variations, though these small variations cannot be identified just in the formal representation. Therefore, I turned these formal representations into the vector space and try to use this VSA, the gradient descent, to match them. Next question is called continuous value prototypes. This is about concepts for each number. The concept is the terminology in Nars. I mean, is it possible for us to create each number a concept? I want to create a concept for point 1, point 2, point 3. How about point 1, 1? It's prohibitive. It's possible. Suppose there are two groups of numbers. Say this is the first group of numbers, 9, 10, 11, 12. This is the second group of numbers, 99, 100, 100, and 102. Is it possible for us to describe as something, some numbers close to 10 and some numbers close to 100? This suggests that with a number, we can find some prototypes between these crowds, and the number can be translated. The number can be represented as a combination of the relationships between these prototypes. Much like in fuzzy logic, we have a membership function. For example, we have this number 9. And we pick number 10 and the number 12 as we have this number 9, and we pick number 10 and the number 100 as the prototypes. With number 9 can be represented as something close to number 10, but is distant from number 100. Therefore, we turn this continuous value into two categorical representations. Thus, that this continuous value can be involved in the reasoning style thinking, It is this is related to budget closely, and since we need to wisely pick what is a prototype we want to change. What is a prototype? It is. You may think this is a little bit close to clustering, but this is not the case. So the question is the unsupervised. And the prototype we chose, maybe want to, since we choose to represent this continuous balance with some prototypes, we have a purpose. So at least it is supervised, but this is a different story. This is very useful in handling numbers in formal thinking, in logic-based thinking. This now previously we had continuous values, now we just categorical values. And this is also useful when combined with different embeddings. Since different embeddings are vectors, they are long vectors. Probably we can turn this, this is what I discovered I want to use Nars with combined with deep neural networks to generate something. Why? Since it is, I have to say that combined with input with Narcissus, with your knowledge, with your requirement, it will be much easier for you to input natural language. Then these large language models will turn this natural language sentences into embedding vectors. If we can have a method to symbolize these embedding vectors, this will be very good for Nars to process this natural language input directly. Though this is related to deep neural networks, therefore you cannot guarantee the result is credible enough. But at least it offers the way to facilitate Nars to with natural language. With natural language, I think it's much better combined with turn natural language into Narcissus. It is pretty complicated. That's all. Any question? Thank you. Thank you so much. Appreciate. Okay, if you don't have question, let's just turn this mic to Bowen.
Okay, thank you, Tori. And let's move to the next one. Christian, are you there?
Yes, sir.
Okay, you can start now.
Okay.
Christian, you can share your screen now. Okay. Yeah, we can see that.
Okay, so hi everyone, I'm Christian. Sorry I can't be there. I wish I could, but unfortunately I could not be there. So I have two presentations today. This first one's going to be more high level, without too many technical details. And then the next one is going to be more more technical, with some hard data. So this presentation is called Considering Simple Triangle Vision Perception with Eye Movements in Nars. And so I came up with the idea for this presentation when I was reading Donald Hebb's book. And I got to the section where he talks about the self-organization of neurons for perception. And he brought up the simple, pretty much the simplest possible example of perception or visual perception, which would be like recognizing a simple pattern, the identity of a simple pattern. In this case, it's like a triangle. And so I thought, this is kind of interesting, the things he's saying. I can kind of relate them to what I've learned about Nars. And so I tried to kind of reinterpret that section from neural organization to conceptual organization, kind of considering what he said from a Nars perspective. So these aren't necessarily my ideas. These are Hebb's ideas, just sort of reconsidered from a Nars perspective. And in particular, the main idea is how eye movements are used for vision. So just some background about vision in Nars. So we know that usually for machine vision, we use neural networks, like a particularly convolutional neural network usually. But there's also the open question still of how far can we take the logical AI approach to vision without using neural networks at all, which would be really nice for Nars, since an integrated system comes with all of its own issues due to trying to integrate separate systems. So if we could have vision ability in just Nars alone, that would simplify things in a sense. A Nars theory of vision perception was first introduced in 2018 and in 2019 in the sensory motor in Nars and perception in Nars papers. The main ideas were introduced there, but it still required more concrete implementations and experiments. And particularly relevant to this presentation, in these papers, the idea of moving your sensor. So you have obviously sensors and motors. So like your sensor would be like your eye, and motor would be like your muscles. But the eye itself does have muscle attached to it that allows you to move your eyes. So it's sort of a mixture between sensor and motor, or a sensor controlled by a motor. And so these papers introduce an operator called shift, which could be like a built-in operator for a Nars with a vision sensor, and shift would be used to shift vision sensor. So this is effectively equivalent to eye movements. So then in 2022, we actually ran some experiments for vision using just a pure Nars system and got some numbers for a standardized data set, the MNIST handwritten digit data set. And Nars was able to achieve 44% classification accuracy for classifying images of handwritten digits that it's never seen before. So obviously 44% is not state of the art when you compare it to neural networks that have done that task. But it might be state of the art for symbolic systems. I'm not sure. I couldn't find other symbolic like reasoning systems that did this, but it might be out there. So while the result's pretty far from perfect, it's still better than random chance. So for a random chance, which Nars wouldn't necessarily be doing as well as random chance, since it has to execute operations to do anything. So it might not execute any operations at all. It might get a 0%. But if it was doing random, like random chance, you would expect like a 10% accuracy, since there's 10 digits, 0 through 9. But we got 44% classification accuracy, which says to me that Nars vision seems like it could actually be feasible, even for a real world, like useful application, like image classification or optical character recognition. And in that experiment, we used a static vision sensor, which means basically the eye was just fixed, and an image was presented to the eye, or the camera, and there was no eye movements. So instead of eye movements, there was a spotlight window. This was a window of attention which moved around the visual field. So there was like a movement in a sense as the attention window moved around, but the actual sensor was fixed, and so the visual field itself remained fixed. So in his book, Organization of Behavior, Hebb discussed the neuropsychology of triangle vision perception using eye movements. So basically a dynamic vision sensor. And like I said, we're going to try to consider these ideas from a Nars perspective, just at a very high level. And then maybe these ideas could be made more concrete and explored and tested in concrete experiments in future for Nars vision, for example, to improve the accuracy score on MNIST data set. So just a couple assumptions that are made here. First of all, that lines in their orientations or their rotations are taken to be the fundamental components of vision. So if you look on the right, this is basically a representation of the visual cortex in the human or the mammals. And this is kind of apparently what it looks like. So across the entire visual field, the neurons are basically kind of acting like feature detectors. And what they're detecting is there a line? the presence of a line, and then also what is its rotation. And it kind of does this across the entire visual field. So you would probably want something similar for Nars, some sort of image filter, like a canny edge detector or something, to perform edge detections. And that this would be like your primary sensor. Because from these, when you have these lines and you have their rotations, then you can build up more complex perceptions from them. Is this actually the full story? Probably not, because even these are actually learned features in humans and like in brains. But we can take it, but it's such a low level that we can probably take it as like the fundamental unit for building up more complicated perceptions. And the lines are also important because they guide the eye movements. So they're not just important for, features are made out of lines, they also guide eye movements. So when there's a line in your peripheral vision, it arouses a motor response for your eye to move in the direction of the line. And basically what this does is when you look at an object or like a new object, you will follow the contours of the object or the edges of it just automatically. And this helps you to determine the figure versus the ground. And so we're going to consider three separate aspects of vision, or not separate, but three aspects of vision, using the triangle vision for a simple example. The first is learning expectations through your eye movements. The second is the problem of sensory interference. And then third is the case of variable distance from the stimulus pattern. So first, learning expectations from eye movements. So here's the triangle example. So there you have a triangle here with three corners. One's labeled A, one's B, and one is C. And the idea is that the system can move its eye at least between the three corners in the simplest example. So here it's like fixated on corner A. And then this is like supposed to be in the shape of the eye for understanding. It might be like more circular in like a real application or something, because this is kind of a difficult shape. But this red circle represents the central vision or the foveal vision. And this is basically where the visual feature is perceived. And then between this red circle and the purple circle is the peripheral vision. And the features here aren't going to necessarily be perceived, and we'll talk about why. But they're actually going to be used to, like I mentioned earlier, guide the eye movements. So right outside the foveal vision, there's two lines, and they each have about an equal influence about what direction the system's going to want to move its eye. So there's a line going this way, so it might go 50% chance to move up here. There's a line going down to corner C as well, and there's a 50% chance you might move there. So yeah, in this image, it's focusing on A, and then it may move to B or C as it perceives the figure. And so for it to move, say to corner A and then down here to corner B, so it's moving up along this line here. Nars might use an operation like shift, which we talked about earlier, and it might have some arguments in the operator. So say like shift upright, or it might be a quantity for more precise eye movements. But just for the simple example, we have shift upright. And then, so when this happens, it's going to be very fast. So in the Nars memory, or in the buffer at least, you're going to have some sensory events or some activations from corner A. And then after a very quick eye shift up to corner B, there's going to be new sensory stimulations from corner B, causing different activations. And so since we have these concepts or these events from A and B being activated in very quick succession after the eye movement, then Nars can form an expectation between them, obviously, using temporal induction. And so this forming of expectations from these eye movements is like akin to Nars memorizing pattern, not just specific features from the pattern, but again, like the contours of the pattern in a sense, where it's moving, the different parts of the overall pattern. And so this is interesting because given a certain corner or a certain visual feature like this corner A, then the expectations inside the system, once it's learned them initially, it will allow Nars to predict the other features. And so conceptually, this is what your expectation would look like. It's an implication statement where you have something like this visual feature, and then shifting my eye, I expect to see this visual feature. If I shift it in this way, then I expect to see this visual feature. So this is just like a visual example. Obviously, you can't actually have pictures like this in Nars, so it's going to be different. And more concretely, they're going to be logical compounds created using the conjunction, disjunction, and negation. And so in the simplest case, you might just take a conjunction of all the pixels. So say here, these lines are the activated pixels. Like each pixel on these lines are considered active, so they have a frequency above 0.5 because there's an edge detected there. Then the simplest case would just be take a conjunction of all of them. So when I'm looking here, the visual feature is all of the edges anded together. So it's basically a kind of a pixel perfect, in a sense, feature. And now the problem with that is that in a more realistic scenario, Nars will probably not encounter the exact same stimulus pattern or that exact same feature because of changes in lighting or slight changes in rotation or shifting of the feature. And there also might be more possible fixation points. So Nars might fixate slightly to the left or to the right. And so you might not actually ever encounter this exact same conjunction again, this exact same compound. And if you just want to do the math, especially if you have like even like a low resolution central visual field, 10 by 10 pixels is very, very small. But even with a 10 by 10 visual field, and only binary activation, so a pixel is either 0 or 1 only, not even talking about like color vision or anything like that, or values in between 0 and 1. Even with only binary activations, this small patch of pixels is going to have a huge number of possible combinations. So you're very unlikely to come across, if you do a conjunction at least, the exact same sensory scenario. And so what you probably need to do is, other than keeping your central vision window small, you also need to extract feature compounds so that they're more general or more abstract, which makes them less specific, which is somewhat bad also, but also good because you can recognize them in more contexts. And so there's like 3 different methods that I thought about that you could do this. So the first would be to stretch the truth. So we know that all the now truth values are just a matter of degree, so that even if a pixel has a low activation, so if it has like frequency 0.6, which is still technically true, just very, very low truth, or even if it's technically false at a frequency equals 0.4, although sort of towards the middle, they still have some degree of truth to them. So if it's really necessary, it's kind of like squinting your eyes when you look at a pattern. You can use these in feature compounds, but the inclusion of sensory events with very low truth values is obviously going to lower the compound's truth value, the overall truth value. But you can still do it in a pinch. The other option is to take subsets of visual features. So when you have the more pixels of features that you're including in your compound, you're making your compound more and more specific. If you say it's this pixel and this pixel and this pixel and this pixel, you're going to have a very specific compound, which again, you might not encounter that in the future. Whereas if you only take a smaller subset, say just these 2 pixels is what I'm interested in, then that's a compound that will be recognizable in more scenarios, more context, simply because there's less features that need to be active. So rather than just taking your whole 10 by 10 central vision, you might take a smaller patch of that 10 by 10, so a smaller subset of features. And then finally, you could use disjunction, which is different from conjunction. Disjunction means or, and so that's going to encapsulate a larger number of scenarios than the and operator. So, if you have a compound that says, okay, this statement is true whenever pixel 1 is active or whenever pixel 2 is active, that's going to be true in a lot more scenarios than a compound that says, well, I'm only true when pixel 1 and pixel 2 are both active at the same time. So disjunction allows a compound to be true in a larger number of contexts or scenarios. So the basic idea is just to learn implication statements, implication statements through the Aigents. But again, you're going to have a problem with recognizing features. And so you need to strike a balance between generalizing or abstracting the features enough to recognize them in various contexts, but also keeping them specific enough that they're still going to be useful for recognizing the pattern. Because you could have a very general feature that is active in like every sensory scenario, which that's not going to be helpful either. And so what it means for them to be useful for recognizing a pattern means that there's not too many, but also not too few possibilities. So if you have tons of implication statements and expectations, the more implication statements that a visual feature is in, the less useful it's going to be for recognizing the pattern because Nars doesn't know which expectation to follow. Whereas the less expectations a feature is in, it's going to be more specific because if you only have, say, one expectation, one implication statement, it's going to be a highly specific scenario, but it's going to be not perhaps so useful for identifying the pattern in different contexts because it may never come across that exact specific feature or expectation again. So you don't want to necessarily memorize pixel perfect features either. And so that's about features, but then there's also like feature generalization, but there's also the problem of ambiguity. So, for the triangle, if you just had a triangle, I guess it's okay. But if you add, we can add another shape to the mix. So let's say we have this square, this diamond shape, which you can see on the image to the right. And so you'll see that both figures, both the triangle and the square, have this feature P. So if I'm just looking at this feature P, I won't necessarily know what am I looking at. I don't know if it's from the square. I don't know if it's from the triangle. Same with this. This is corner A, and then same with this feature Q, which is this edge between corner A and B. That's also common between the two figures. And so just looking at those features alone, we can't really tell what figure we're looking at. On the other hand, if we're only considering these two figures at least, this feature TB1 and TB2, these are highly specific to the triangle figure. So if I see even just this one feature, TB1, I already know I'm looking at the triangle. Or TB2, and not the square because the square doesn't have these features. Now, of course, Nars can't determine which features and expectations are going to be useful up front, and so those need to be refined. And also the evidence aspect of now solves part of this problem automatically because Nars is going to be from the various visual features deriving and pooling many different possibilities about the identity of the figure, and they're all going to have different truth values. And so when giving an answer, Nars can just select the one with the highest truth value or the most evidence, especially for executing operations. So just for a concrete example, let's say that we're exposing Nars to the triangle pattern and the square pattern. And with each pattern, we're giving it the label. So when we show it the triangle, we're saying this is a triangle. We're showing it the square, we'd say this is a square. And we give it these labels so it can form the associations. So then in the future, then we show the patterns again, and we're trying to say, okay, Nars, what is the identity of this figure? And so it might look at, say, figure P, and it's going to derive, it'll have seen figure or feature P in both contexts for the square and the triangle. So it's going to derive the label square and it's going to derive the label triangle. So it's sort of ambiguous. And there's like two options in its head, what could this figure be? Now, at least, we know it's not going to be a circle because these are lines, not curved lines. So at least, some figures can be excluded, but at this point, it's still ambiguous. But then when Nars looks at a different feature like this TB1, that's going to derive only is triangle. And not is square. And so this label is square is going to have a lower truth value compared to is triangle. And as Nars looks at the figure for an extended period of time, say it's looking at this triangle, some of the features might be ambiguous, P and Q, but then these other ones are going to be more identifying, this TB1 and TB2. And so there's going to be more evidence on the whole for the triangle label than the square. And so that's how it could correctly identify the figure. And this was the basis behind the MNIST experiment. And so the singular features can be useful for identifying the figure. But with the eye movements now, because we're talking now about adding eye movements into the vision, then Nars can additionally use these confirmed expectations and anticipations for identifying the figure as well. So if this feature P is just too ambiguous to make a full prediction, and let's say even this feature that we said was very specific to the triangle TB1, in the simplest case where we have the triangle and the square, yes, that's true, that will help identify the triangle. But in a more realistic scenario, this could belong to any other number of shapes. This could be like the fin of a shark or something. So it's not necessarily we can just look at one feature and say, yep, that's a triangle. But if Nars does start at P and then performs an eye movement and sees TB1, now it's going to be more confident that it's seeing a triangle because it says, okay, I saw this feature here. And if it's a triangle, then this other feature should be located at this part in space. So let me move my eye and look. And then when it looks, if it can confirm that, then it can say, okay, yep, this is a triangle. And if there's many confirmed expectations, now like one time is good, but if you do this many, many times, then it will become more highly confident about what the figure is. It says, okay, and now I move my eye down to C, I expect to see this type of triangle shape. And if it does, I can say, okay, I'm almost certainly looking at a triangle. And then finally, there is the case of differing distance from the stimulus pattern. So obviously, in an actual realistic scenario where the agent is embodied moving around the world with its vision sensor, the agent is going to be almost always at a different distance from whatever the stimulus pattern is. So as it moves around the world, it might be closer, it might be further away. So like on this image, this pattern is very far away from us, which is why it looks small. And then this one here is larger because it's closer. And so you can see that the two figures are, they're the same, they're similar, but they're going to be creating a different sensory impression on the retina, on the eye, simply because they're larger, so it's going to be activating different neurons. So the question is, so how then do we see that these two shapes are the same if they're doing a different activation in our eye? And here again, the idea of eye movements and corners or lines is very important because it gives a good reason why to focus on corners in central vision and lines in central vision and to sort of ignore the peripheral. So if you look at this image to the right, the red circle again indicates the central vision. And look at the features inside the central vision when the pattern is far away. And then on the right, when we're closer to the pattern, look again in the central vision. Both of these eyes are fixated on corner A the whole time, and yet it doesn't matter what distance you are from the triangle because the pattern in the central vision is going to be exactly the same. So the visual features are going to be exactly the same, which means that Nars could match this pattern regardless of the distance from the triangle. It can match that and say, okay, well, this looks the same. And it really won't even notice too much of a difference. At least when it comes to central vision. When it comes to eye movements, you might have to move your eye quite a bit more. So that's a different story. But at least for when it comes to the image features, they're going to be the same in central vision. And this is true for any rectilinear pattern. And rectilinear means a pattern composed of straight lines. And so this kind of makes the issue almost moot, since it doesn't really matter how far the agent is from the shape, as long as it's fixating on the corner. And there's also, while the pattern outside the central vision changes, it changes predictably. So you can see that this line, as we get closer from A to B, extends outward. And then as we get further away from the shape, the line comes back inward, which is why it looks smaller. So the pattern in the peripheral vision, the line changes predictably. And what's cool about this, the fact that the two central vision patterns are the same, this introduces a form of stimulus equivalence because the two stimuli are technically different, but they can be recognized as having the same features and the same identity, which is triangle. Now, for curved figures, it's not going to be quite such a simple answer because the pattern in the central vision will change with the distance to the overall pattern. But we can, you can partially resolve this problem by choosing to fixate on corners and straight lines in your system design and sort of ignoring the larger curved patterns. So in conclusion, the eye movements, or doesn't necessarily have to be an eye movement, it could be the entire head. But the movement of the visual sensor is important for vision because it allows the agent to focus on different parts of an object using the same sensory cells. And there's three aspects of eye movements that we want to consider for Nars vision. The first is that during eye movements, the system should be forming expectations in the form of implication statements with the operation, and that will allow it to make predictions and perform pattern recall. The second aspect is sensory interference occurs when features obscure the identity of the overall pattern, but the system can learn to effectively ignore sensory interference over time by refining its expectations. And then finally, the distance from a pattern changes how the pattern appears, and that can also obscure its identity. But the system can overcome this by focusing its central vision on rectilinear parts of the pattern using eye movements. And my hope is that by enhancing Nars with eye movements, it'll have the possibility to improve Nars native vision, and especially to improve the score on standardized data sets like MNIST digit dataset. And that's all. And here are my references. And thank you very much.
Okay, thanks. Thank you, Christian. So anyone has questions? No. Oh, Christian, I have one question. So
yes.
Do you consider the case of distortion? Like, although you have a triangle, but the location of each angle will just change slightly.
Mm-hmm. You mean here?
Yeah, so it's not the size, but the shape would just change slightly, but it's still a triangle, and like you can just rotate one angle, or just distort. Like it's a distortion, not size. I mean, for example, you can have a make the change the location of A while keep the locations of B and C, so that the shape of this triangle will change slightly. So do you consider this situation?
I don't fully understand. Do you mean this is just about the distance from the pattern, not distorting the pattern at all? So, like having a different pattern would be a different scenario.
Yeah, but you have several patterns, but they are very similar. Like,
they all have
corners. Yeah, but they are similar, but it's not the size, not the issue of size, but the issue of shape. They are all triangles, although, but you can change the locations of each angle. Like you can change the location of A or B or C slightly, and it looks like a triangle, but it's different from this triangle in your.
I think it would have to be memorized. I'm not sure, but I think it would have to be memorized as even a different shape, like a different kind of triangle.
So do you mean that this model should memorize each of the possible cases, like each of possible shapes, although they are similar, and although they just
change slightly, but you have to store them as multiple patterns.
Sort of, yes, but that's also why I brought up here that you probably don't want to save pixel perfect features because like you mentioned, even a slight distortion, now your feature, you don't recognize it anymore, even if you have a slight distortion. And so that's why I recommend using things like disjunction or taking smaller subsets. And then in that way, like disjunction, for example, can be used like if the feature is slightly shifted left or right, it can be used to recognize that feature, even if it's like 1 pixel to the left or 1 pixel to the right. So there are like some methods, I think, that can be used to make it more flexible. But I think if you have a large degree of distortion, then you probably need to memorize it as a separate pattern or feature.
Yes. Okay. Okay. Got it.
Thank you. It's a good question.
Yeah. Thank you. So no more questions. Okay. So let's move to the next talk given by David Ireland. He's the senior scientist from Australian eHealth Research Center. So David, are you there?
Hello, I assume you can hear me?
Yeah.
Yeah, okay.
Okay,
I'll just
here you
get
go.
on the slides.
Okay.
Sorry, I don't normally use Teams. I just have to allow it in the permissions. And I'll just have to reopen Zoom. Oh, sorry, Zoom. I don't normally use Zoom. I just might have to relog in. So bear with me. Sorry about that. Sorry about that. Can you still hear me?
Yeah, I can hear you, and we can see your screen.
Okay, great. So, hello from Brisbane, Australia. Just to give you some background, I am a computer scientist that works in the health domain. I work with doctors, therapists, clinicians, and building and trialing technology to help people living with conditions such as autism, chronic pain, opioid addiction, and other drug addictions and dementia. I build chatbots, web portals, and I do studies on human-computer interactions and do a lot of natural language processing. So while I am a researcher, I don't work at a university. I work at an organization called the CSIRO. This organization is an Australian government agency, and we do research in most science fields from agriculture, science, technology, and energy. And I, of course, work in the health section. I like to use my own implementation of Nars, which is written in the Common Lisp language, but the inference rules and theorems are for the most part taken directly from Professor Pei Wang's book. There are differences in the control system, but I do make use of bag data structures. But one of the novel things I experiment with this is connecting the knowledge base up to the underlying garbage collector of the virtual machine. And I also do, my implementation is thread safe, so I also do experiments on parallel operation. I'm happy to share the code for this. Just send me an email. But today, I'll be talking about Nars in the health domain. This won't really be a talk on AGI, but rather a very practical case of using Nars. I am, however, very interested in AGI because it involves the intersection of many fields that interest me, from philosophy, psychology, etc. But in reality, in my country at least, there are no grants. So my approach in AGI research is to include my work in health research as much as I can. And that's what I'll talk about today. The following slides I'll show you, which I just presented at a health conference on using Nars in the area of what's called precision health, where I've used the case study of chronic pain management, where I think Nars will provide a more insight into the state of an individual opposed to mainstream machine learning. And I think this funny comic summarizes the problem we have in health when dealing with an individual living with a specific medical condition. So in the comic, we humans have put down the AI uprising, which turned out to be much easier than expected. And the person on the left wonders why they use rocks and spears, and the person on the right explains in the historical data, rocks and spears won the most battles. And the point is the statistically expected value from a larger data set is not always reliable for an individual in the context of real life. So I do projects in what's called precision health. This is a notion that takes into account the person's genes, lifestyles, environmental factors, and behavioral factors in the person's healthcare. It has become very popular now that mobile apps, wearable devices are commonplace that track every major bodily function. And the argument I've been making for some time is that in some cases, big data and associated AI isn't really precise with an individual in mind. I need an AI system that thinks about the individual. In the context of precision health, it would probably first have to function with an almost empty knowledge base and begin learning in real time as it receives more data from the user and therapist. Its conclusions need to be explainable and they need to be revisable as more data comes in. And to justify this, I'll use the treatment and management of chronic pain as a case study and show how Nars fits these requirements. So in my country, 20% of Australians living with chronic pain. This is pain for more than 3 months from a variety of causes. It could be trauma from a car accident, or it could be some underlying medical condition like cancer. Australia has a free health system, but this means it's often overloaded. And chronic pain is a complex, common, and expensive health problem, and often incurable. It is also the main reason in my country why people seek medical care, and there is limited pharmaceutical treatment for long-term management. The medications, or what are called opioid medications, like morphine or endone, are typically used for severe cases, but ideally for the short term because addiction habits can form from long-term use. In fact, in my country, there's been more deaths from prescribed opioids than illegal drugs. And I know there's an opioid crisis in the US from the overprescription of these medications, and my country is going down the same path. The problems we face, however, if we don't provide effective pain treatment, people start turning up to the ER, and that gets overloaded. And in Australia, we only have a small number of sites providing specialized pain treatment that is free. And the reality is that in most of these cases, we can't really reduce their long-term pain. But there are interventions that can manage it through behavioral changes and medication management, usually by a therapist who's well acquainted with the client's pain history. So I collaborate with clinicians at a pain and research centre in Australia that operates in a major hospital in my city of Brisbane. There's about 1,000 people on the waiting list at any given time to get into this clinic. It is an outpatient clinic. It is publicly funded, and it treats and researches people of all ages living with chronic pain. And my work is on the development of technology that collects data to help the clinicians. I build mobile apps, web portals. I do studies on gamification, chatbots, and other machine learning projects. I am very much interested in children that might have a language disorder and they can't communicate their pain. We have built a digital platform called Pain Roadmap, which consists of a mobile app, pain diary, a clinical portal, and what we found in a pilot study that the use of this technology reduced, we had a 30% reduction in opioid medication. It also collects data from wearable devices to measure gross body movements, but people don't like being monitored or constantly entering data in the diary. So we normally ask them to use it for 1 week at a time, where it gets reviewed by a therapist. So this is the main screen of the mobile app that the clients use. We ask the clients to report on the app, their medication use, behavioral activities, like what they're doing, and their pain levels. And here's a simple activity data. So we're interested in the activities that might be aggravating pain, and they might be walking, but they might be walking going to the shop. So we're interested in associated metadata as well. And we also ask people when they think they've overdone it. So they log their pain from a score from 0 to 10 and any associated sensations that they are feeling. And then the therapist views the data on a web portal. And this is a screenshot of a single day of data. It's real data. And then the red lines donate pain throughout the day. The blue lines are the accelerometer data, which is measuring the gross body movements. A description of the activities is labeled for each time of the day, and the red ones are when they've said that they've overdone it. And the medication types and when they've taken is also placed on the graph. So from this, the therapist tries to find behavioral trends that might be aggravating pain. How are they using the medications to manage that pain, and how effective these medications really are? Some people will numb their pain with medication and then push their body to their limits. In contrast, some people will take strong pain medication and just remain immobile for long periods of time. Both extremes aggravate pain, and it requires a lot of investigation by the therapist, who only has a short time frame to help their patient. So I have a research interest on creating and deploying an AI assistant for the therapist. It has to deal with incomplete data that arrives piecewise, often separated by weeks, and often contradictory. It has to be revisable, as medication changes can either improve or worsen a person's situation. Moreover, tolerance to opioid medication gradually increases. This means that long-term use for opioids, they often need more and more to sort of to dull the pain sensations they're feeling. It also has to be explainable. As the therapist in my country, at least, the therapist is liable for their decision-making, particularly when reducing opioid medication, which can result in the suicide ideation of the patient. So it's not just simple as just taking the medication away, because the suicide rates will basically go up. We found pre-trained prediction models have limited use, as the data of another person or even a group of people is not that useful when treating for a particular patient. There is a lot of medical, social, and cultural context that needs to be taken into account. My country is very much made up of many different cultures. So, for example, we have to take into illicit drug use, sexual activity, and the person's attitude towards pain and their tolerance levels and their history of drug-seeking behavior. So I, of course, have been working on Nars as the AI assistant, and I've been trying to explain to Nars, to health clinicians and other data scientists and other colleagues in machine learning how it works, and this has been quite a challenge. And ChatGPT has really not helped. So I'll quickly just go through how I presented it recently at a health conference, and then I'll return back to the case study. I do apologize if you know a lot of this already, but I think effectively communicating how Nars goes about things, why it's different, its strengths and limitations, for me is very paramount in expanding sort of with new collaborators and projects. So I typically start with Nars having a long history in AGI research, and it attempts to be a normative theory of intelligence. And of course, AGI has only recently become popular nowadays, thanks to ChatGPT. But the fundamental difference with Nars, of course, is it assumes there is insufficient knowledge to questions that it needs to answer, and intelligence is what merges to deal with this. And I liken this to animal intelligence adapting to its environment, which I find much more interesting than the notions of superintelligence or the singularity. This assumption is, of course, in stark contrast to typical data science practice, where ideally we obtain a good quality data set and then go about to create a model to make predictions or understand the relationships captured in the data. I can assure you, at least in Australia, a clean, good quality data set in healthcare is a very, very rare find. So Nars' strength is that it starts from a blank state and then it works iteratively. And we can seed it with information, some a priori information, but for the most part, it's a blank state. The logic convention of Nars, of course, is significantly different from predicate and propositional logic from what we learned at university. And it uses term logic, which was first formalized by Aristotle 2,000 years ago. This convention has been largely forgotten, except in philosophy. But what I think its strength in term logic is that it describes and reasons on the relationships between terms. And we also have concepts, which are the data structures that identify a term in a running Nars system. So the two basic statements in Nars' term logic is, of course, S is a special kind of P to some certain degree, and S and P are similar or interchangeable to a certain degree. There are, of course, many more complicated statements and operators, but for the case study of chronic pain, I believe this is all we need. So, of course, we know in Nars, every statement has evidence that is quantified by the frequency and confidence. These make up the truth value. In my experience of presenting Nars to a health audience and a machine learning, this is where they get very confused. So in explaining the truth, I found this figure very useful, which I actually borrowed from a paper written by Dr. Patrick Hammer. And it does seem to be a figure people can understand. And I state that a belief statement in Nars has a truth value somewhere on this plane, and this point moves usually towards the green regions as the system receives more data or learns from its knowledge base. The truth values are, of course, from evidence or truth functions, and the evidence could be from observations, which in my case would be the Nars reads the pain app diary. It looks at all the activities, their pain level scores, or from an inference pattern where a truth function is applied. And of course, the y-axis is the frequency, the ratio of the evidence that supports that statement over the total evidence that supports or denies the statement. And the x-axis is the confidence, which quantifies the amount of evidence accumulated so far. Confidence, actually, I'm finding very useful, as I'll show you soon, as more just not just in accumulating or quantifying the number of evidence. So the question I get at this point is, how does Nars learn when it actually has incomplete data? And the answer I like to give, it creates a conceptual graph of all its beliefs, and it sees where things connect. This, of course, is very simplistic and not entirely true, but I think it effectively communicates the point. Of course, when two statements connect, they share a common term, and via reasoning, new knowledge can be created. Where the common term is located determines the mode of reasoning, such as deduction, induction, and abduction, and what truth function to apply. We all know deduction is deriving specific cases from the general, and is a reliable form of reasoning and commonly used in mathematics and statistics. Induction, of course, is making generalizations of specific cases. The example I like to give is John is a grandfather. John has gray hair. Therefore, grandfathers have gray hair, and of course, with the much lower confidence. We also have abduction, which has several interpretations, but it's commonly associated with finding an explanation for a state or an event. I really do intend to find better examples here, because I think abduction is a commonly used technique in medical diagnostics. If you have any better ones, let me know. So deduction is what should be true, induction and abduction are what might be true. And of course, the scientific method is a combination of all of these modes of reasoning. And we have revision, which is when the system sees two statements that are the same, but derived from independent evidence. And then we can derive a conclusion, which is the truth value merged from both statements. And this allows the revision process allows uncertain beliefs to become stronger and provides balance for conflicting evidence. At this point, the most common question I get is, why aren't we using probability? And why are we using these heuristics for truth? And my response to this, as I first point them to the probabilistic logical networks that also use the same term logic convention. Of course, we can use Bayesian networks, but the main reason I give is that we just have the assumption of insufficient data and knowledge and resources, and that means the axioms of probability can't be satisfied. From memory, it's the third axiom, which requires a consistent probability distribution for each statement. And Nars doesn't have this requirement, and so we can, of course, assign different truth values to the same statement with different evidence, and the system is entirely stable. Also, I also make the point that there is actually multiple interpretations of probability. We have the frequency interpretation, which is found in statistics. We have the subjective, the degree of belief, also called the Bayesian interpretation. And we have the logical interpretation, or the degree of evidential support. The heuristics of truth used in Nars has elements of all three. So in my opinion, we get the pros of all these interpretations, but the truth value isn't defined by a single one. I do know there is a big debate on using probability in AGI for general reasoning and under uncertainty. But I think the confidence heuristic value here is very much underestimated as a useful metric. And I'll show you soon how I'm using it specifically in chronic pain. So returning back to our case study, the activity and medication data that we capture in the pain roadmap can be encoded into Nars using these just basic inheritance statements. I've been breaking up the day between the dawn, morning, afternoon, and evening, and these, of course, are concepts in the system. I make use of terms that are composed of other terms. So, for instance, we have morning and the 10th of January. This is really useful when the therapist might want to ask questions. For instance, what activities are just happening in the morning on any given day. I can, of course, use any time scale I want. And the clinician might might be interested in just the AM or the PM or just on particular days. So I think this scales very, very well. And we can formulate these expressions quite easily. The frequency component of the truth value is proportional to the fraction of time spent undertaking the activity. While here the confidence is still, I'm just set to default of 0.9. For example, if they were driving for half the morning, the frequency would be 0.5. For medications, if they start their medication at the beginning of the time period, we would set the frequency to 1. But if it's in the middle of the morning, it would be 0.5. So, for example, if they say if they're running or exercise, going back to the confidence, even though I set it to a default of 0.9, what I think could happen is we often use the accelerometer or the wearable device to see if they're really telling us the truth in the diary. Often most people actually do tell the truth, but if they're saying that they're running or jogging or walking and the accelerometer is flat, we know there's a bit of doubt there. So that's where we could adjust the confidence. I haven't quite sort of got it yet, but that's where I think there'd be a very nice use for it. As for pain, we can encode it. We can encode it sort of very similar, and where the pain is normally logged as an integer between 0 to 10, which we could map to 0.1 for the frequency, and the time period is sort of inherited from pain. And the frequency is, so typically we have multiple pain scores throughout the day, and these would just be revised into an average value. I've also found when asking people how much pain they're in is not as easy as it seems. Studies have found, and we have found this as well, that if we ask a person to quantify a pain event that occurred at a much earlier time, then the brain recreates this sensation and then over-exaggerates it. And higher values are then recorded in the diary. So ideally, we want pain logs as the sensation happens, but this isn't always practical. So we can adjust the confidence of pain statements based on the time gap between when the pain level was logged and when the event actually occurred. So here is example data of this conceptual network formed by Nars, and this is real data, but a subset of it. It's just for one day, and Nars has only just read the diary data for that day and loaded it into the system. The person has on average a pain score of around 7 out of 10, both for the morning and afternoon. And the average, that was just derived from multiple pain logs throughout the day. So when Nars begins running, it uses its reasoning patterns to create associations between the actual activities like train traveling, sitting, driving, and walking to the concept of pain, with the truth values giving the strength of these associations and the confidence of this strength. So here the train traveling has the highest frequency to pain, but the actual cause might be sitting down or it might be standing up. But it's just sort of identifying train traveling has the highest association. Also, the person took a very strong pain medication called Tramadol at the beginning of the morning, and even though the person is still reporting moderately high pain, we would ideally want to see a very weak association between the concepts of that medication and pain. These associations, of course, would revise as more days are entered, and as medication behavioral trends are tweaked by the therapist, we'll see this change, probably quite a lot. And from this, I believe the therapist can identify activities and medication effectiveness from these associations. We can, of course, do predictions by creating a hypothetical day. This could be done by the therapist, and we can attach some activities to this hypothetical day, and then Nars will make predictions to the concepts of pain, and it can also do it to the concepts of overdid it. We found that the idea of when someone says they've overdone it, the definition is very specific to that individual. So people with higher tolerance pain levels will, of course, will less frequently say they've overdone it, while many people will actually, with low tolerance, will just report it all the time. So this is very individual centric. And of course, these predictions are explainable, and they will definitely change as we get more data. What is very interesting is that we often get people put in the diary something we didn't expect, or unrelated, or directly unrelated to chronic pain, and that might be that they're depressed. And what is very cool with Nars is once that concept goes in, it immediately begins creating the associations with the other concepts. And here it's sort of looking at how interchangeable depression and pain are for this particular individual. Because depression is a mental state and physical pain, and pain is a physical feeling. And like depression, it can mean different things to different people. So what I'm finding is resonating with clinicians and using Nars is that what Nars, the system, perceives as truth about a person's situation is based on the relationships between the concepts, such as the train traveling, they're sitting, whether they've overdone it, what pain level they're in, or how depressed they are. And it's not based on any implicit conditions or a priori beliefs, which might include cultural or contextual biases. So each conceptual network formed by Nars will be unique to the individual. In the near future, we will be embedding a Nars system into the roadmap platform for an opioid tapering randomized control trial, which will be starting next month, and that will be an AI assistant to the therapist. The therapist will be reporting how useful the system is and whether they agree with its assessment. Of course, the pain therapists can't be expected to know term logic, so I am busily working on a natural language front end. This front end will also include a chatbot, which we, in the long-term future, will use it as a virtual pain coach for the actual person living with chronic pain, where they could ask, for example, I've just taken my endone, I'm going to go mow the grass, how long before I overdo it? So just a plug for tomorrow, I am doing another talk at this conference on language acquisition in Nars. And if that interests you, I hope to see you there at 2:50 p.m. your time, which is about 7 a.m. for me. And that's the end of my talk. Thank you for listening.
Okay, thank you, David. So any questions? Yeah, you can come up.
David? Awesome use of Nars Really cool to see how you're kind of like using it in a non-canonical way, I would say, like using just the inheritance and similarity, but it seems to really work. I like that frequency is like related to activity length. I think that's really cool. I had a question, and I think you answered it at the end there, but I just want to make sure. So when presenting, this system to the doctors, right, like to the clinicians, like you rightfully said that they're not going to know term logic, or you're not going to show them the concept graph. Like, so what's the interface that you envision to communicate whatever Nars concludes, or I guess like what it infers? How do you see presenting that information to the clinicians, and like how would they interact with it? Is it through the chatbot?
It's an excellent question. Those graphs that I was showing, they actually like that, by the way, and the connections. The clinicians I work with are very busy, and they just want it has to be very simple. I don't think it'll be like, I think the chatbot will be for the end user. I think the clinicians just want a list of like really simple one activities connecting to pain the strongest. But to be honest, the trial that we're running, I was lucky to Nars is like an add-on to it. So there is like a primary intervention, and then they, because I work with them for a long time, they let me tag things on. So I think it's going to be a part of the trial is how do we convey the information Nars is giving back to the therapists. So I think it'll be what we call co-design. So I'll do what I think, and then as the study things, I might sort of vary it. So does that answer your question?
Yeah. This is just like I said, as you were showing this, I'm like, how do you convey this to non-technical audience and on that topic also? Like, thank you for presenting, sharing some of the stuff that you did earlier. That's also a good way to tell other people about Nars. So I think you nailed it. So, thank you.
Okay, so let's move to Christian again, Christian Ham. We can start now. Christian?
Okay. So this is going to be a little bit of a shorter presentation, and maybe a little bit more technical than the last one that I gave. This is a project I'm working on with Mina. So shout out to Mina for, first of all of his hard work on this project, because he has a really good understanding, deep understanding of everything it entails, and also for making most of these slides. So thank you. So this presentation is called Knowledge Graph Embedding Transformation with Nars. And the basic idea behind this project is, can we use Nars to improve performance for tasks over knowledge graphs? So for anyone who doesn't know, a knowledge graph is basically exactly what it sounds like. It's a graph that contains various pieces of knowledge. And more specifically, it's a structured network that has entities and relationships between the entities. And so you can use this graph as sort of a data set of knowledge to help, or to allow machines to understand like human declarative knowledge. So the knowledge graph will have a certain number of entities and entities and a certain number of relations, usually a very small number of relations compared to the number of entities. So you might have tens of thousands of different entities and maybe like 15 unique relations. And each of the facts or the pieces of knowledge in a knowledge graph are stored as a collection of triples. So you can't necessarily have like a graph stored in a file necessarily, unless you have like a certain format. So the way that it's standardized is that you have like a text file, and 3 columns. And so you'll have your, and so each line is a triple. So there's 3 components to it, which is the head entity, the tail entity, and then the relation between them. So the head is sort of like the subject, the tail is sort of like the predicate or the object, and then the relation is the relationship between those 2 entities. So for example, you might have an entity Albert Einstein and an entity theory of relativity, that's your tail. Albert Einstein is your head, and then a relation between them discovered. And so this would be a triple representing a piece of knowledge that Albert Einstein discovered the theory of relativity. So that might be like 1 line in your text file. And visually, this is what a knowledge graph looks like. So each of these nodes represents an entity. And then if 2 entities have a relation between them, there's a link that's labeled with the relation. So like a knowledge graph might have Ohio is a part of the USA, Pennsylvania is a state part of the USA, and each of these is a state. And so your relations are this label part of, and this label is a, or you might have another relation like lives in. So Bob lives in Ohio. Bob is a human. Bob has a house, which is good for Bob in this economy. But so you can see that the relations can be in different parts of the graph. So even the same relation. So Bob is a human and Ohio is a state. And these entities aren't necessarily linked to each other, but they share, they're using the same relation. So these relations can be used in various different ways to represent knowledge. And the idea is that we want to use Nars to either to process the knowledge graph, because Nars has a conceptual network as its memory. So we already have a network data structure. We might be able to sort of transmute the knowledge graph network into a Nars memory network. That's one idea. The other idea is to just use the logic of Nars to augment the original training set, to augment the knowledge graph. So like as a simple example, you might have Bob lives in Ohio, and Ohio is part of USA. So, using reasoning, you might be able to do something like deduction or some sort of reasoning where that Bob lives in the USA since Bob lives in Ohio. And then that might improve the performance of machine learning techniques on this knowledge graph. And that's what we did here. So we use a machine learning technique called the translational distance model, or TransE. And this is a embedding technique, and it represents the entities and relations as vectors, not as symbols, but as vectors in a continuous vector space. And the idea is to model the relationships between entities as translations in the vector space. And so more technically, the plausibility of a triple here is the distance between the head vector. So you're going to be converting all your entities into vectors, all your relations into vectors. And so if you add the relation vector to the head vector, it should equal the tail vector. And that's what the machine learning technique is trying to learn in embedding, such that when you have a specific head entity and you add the relation from the tuple, then you're going to have something that's at least close to the tail vector. And obviously it does this by minimizing a loss function using this formula here. And there's actually 2 parts to this loss function. So for this specific model, TransE, and there are other models that don't necessarily need to do this, like one called Conv. But for TransE, it requires something called negative samples. So you have your training set, which has all of your knowledge for your knowledge graph. And those are called your positive samples. And then you can use certain sampling techniques to corrupt some of this knowledge and get what we call a negative sample, which is basically if it's not in the training set, then we assume it's negative. So the system should learn to basically get as far away from that sample as it can, while getting as close to the positive samples as it can. And the number of incorrect triples or corrupted or negative samples is usually much larger than the positive So we used a strategy called the Bernoulli distribution strategy for negative sample generation. And again, basically you're just replacing either the head entity or the tail entity based on some probability and some random selection to change the true sample, what's positive and what's in the training set, into something that's not in the training set, and then assuming that to be a negative sample. Although that might not necessarily be true, but that's the assumption that's made. So we basically did this standard Bernoulli strategy, and then we also augmented the training set using Nars by deriving new pieces of knowledge and then sticking it in the training set. So then now, first of all, those samples, we're going to generate negative samples for those, but also it's going to be giving more potential positive samples. And so when we're generating negative samples, if Nars has already generated a piece of knowledge saying, no, this is actually positive, then we're going to ignore that negative sample. So it like reduces the number of incorrect negative samples is the idea. While also simultaneously increasing the number of positive samples. So kind of two benefits there. And so we're trying this on various data sets, but for this one, we use the FB15K237 data set with these hyperparameters. And yeah, you can read these if you're interested. So with the baseline burn method, this is what our results were. So given a test set, it's going to, the test set also has triples in them with a head, a tail, and a relation. And then for testing, what you do is you kind of obscure the head or the tail. And then the machine learning algorithm will predict what it thinks the head or the tail is. And actually, it will make many different predictions. It'll be like ranked based on how close the vector is. And so that's what these columns here mean, H at 10, H at 3, and H at 1. So H at 10 means that the system returned, the machine learning system returned 10 possible answers. And then there's only one correct answer, which is the one in the test set. And so if any of those 10 answers were correct, then that's a positive for the hit at 10. So, so the top 10 returned answers, as long as the answer is somewhere in there, we consider it correct. Whereas H at 1 is much more strict. So that's saying basically the system needs to return the optimal, the test answer in the top one. Like it has to be the closest vector. So that's much more strict. And so then you average the head and the tail metrics. And so this is basically what we're interested in, which is the average between them. And so this 0.39 for hit at 10 means that for 40% or 39% of the test examples, the system was able to get it correct by returning the top 10, its top 10 answers, and the answer was contained in that set of 10. Same with 3, the system returns 3 answers, and the correct answer was obtained in one of those 3. And then 15% for hit at 1. So about 15% of the time, the system was able to return the optimal correct answer according to the test set. So then the question was, can we improve these numbers with Nars by augmenting the training set with positive samples? And this is the very simple method we used. So first of all, we loaded all the knowledge into Nars using the product and the image operators for the relation. And then we performed some analogy and applied the analogy and comparison rules with 2 related statements. So this is like a really easy visual that you can follow. So say we were given a test tuple saying, and we ignore the head, we're obscuring the head, we say, who works at Acme? And the knowledge graph might say, well, John works at Acme. So we already know that, but that's all we know. Who else works at Acme? And so what we would do is we'd start at the subject, which here is John. And then we would move to a different relation. So instead of working at Acme, we're going to just move to a different predicate that John has. And this says John lives in USA. So now we have a different predicate that we started with. And then from this predicate, we search for another subject. that's in the Nars knowledge. So here, John lives in USA, but also Bob lives in USA. And so from those two different statements, we can say, okay, well, if John lives in USA and Bob also live in USA, then Bob is similar to John. And then you can apply that to your original statement, John works at Acme, and Bob is similar to John. So Bob, we can infer that Bob also works at Acme. And this is the basic idea behind the positive sample augmentation. And the result from that was actually a slight improvement on the quantitative metrics. So this is the baseline from the previous slide, which we already went over that. But with the augmented data set, then we actually do see an improvement in the numbers. So in the old hit at 10, we had 39% accuracy, and in the new, we're getting plus 4%, so 43%. And then on both the hit at 3 and the hit at 1 metric, we're seeing not very significant, but it still is there, improvement by 1% increase. And so this was just a very quick, very simple and naive approach, simply just doing the same analogy and comparison inference over and over on various pieces of knowledge in the training set without any other types of inference. And simply by augmenting the data set with these generated tuples, we actually did receive a quantitative improvement on the machine learning technique. And so we're hoping that in the future, we can do more types of inference, maybe more sophisticated types of inference, and to be able to improve these numbers further. And so, yeah, it looks good, but there's definitely still more work to be done. But at least these preliminary results show that it is possible to get improvement using Nars. And that's all.
Okay, thanks, Christian. Thank you for your talk. Any questions? I think there are no questions on them.
Okay, thank you.
Thank you, Christian. So let's do the next one. Next speaker is Dr. Kai Liu. He's from Bohai University in China. And yeah, you can start.
Okay.
Okay.
Oh, hello everyone. Can you see my screen? The PPT.
Yes.
Okay. Thank you for your invitation. I'm honored to attend Nars workshop and report my work here. My name is Liu Kai, and I'm working at the School of Education Science at Bohai University. I also serve as the director of the AGI Research Institute here, and I am the organizer of the Chinese AGI Society. 8 years ago, I had known and learned Nars under the guidance of P1. Today, we can probably say that Nars has moved beyond just being an experimental prototype system. It officially started its industrial applications. And that's exactly what this report is all about. I will introduce the following topics in sequence. Firstly, I want to clarify the essential issue with the application of Nars from a theory view. Actually, it's a paradox for us. Then I will show a real industrial customer demand to detect the steel crack before they are shipped out of the factory. Next, I'm going to propose an application model for Nars and give our solution for Nars application. In the end, it's our future work on it. Okay, let's go to the first part to meet the weird question. So we all know that MLM is not a real AGI attack. I forgot to open my camera. Yeah. They are AGI, but not they are SAI, specialized purpose AI, but not AGI. A typical SAI system aims at the precise purpose. However, a typical AGI system didn't meet any practical purpose at all. So the hardest question is how to make a system that ignoring application goals mostly, but to pay most attention on it. It sounds like a paradox. In the fact, we have two approaches to solve this problem. One is educate Nars as a child. The other is use Nars as an inference tool. There are differences between the educate a robot child needs a lot of time to coding and training. While use Nars as a tool is relatively fast and not that hard to do. So we can say the first, the education approach of Nars application. This approach requires the following conditions. Those are not easily to achieve. However, it is the real and pure AGI solution. As far as I know, the most important of all, Nars needs a physical body to adapt to application environments. Then it should have a control mechanism to meet application needs directly. What's next to do is let Nars robot grow up continuously to know the physical and human world. Well, there is a multi-sensory system could manage the one, the two, and the three. So it is a tough work and has a long way to go. However, that is just what I'm interested in and my team's research direction. The two approach is easier, faster, and more efficient because it is project demand centered. With the traditional way to solve problem, it is needs some extra works to be done. I call it systematic specialization. The goal is to fully customize the Nars system. In other words, make the AGI system Nars to be a SAI system. This will be discussed in part 3 and part 4. In this section, I will introduce a real industry demand. In any steel factory all over the world, to check steel quality is an important work. There are huge demands under this task. Here is a common defined types of steel. I'm not familiar with this defined name, so I did translate those labels into English. But what we are about is a crack in the steel. That means we don't solve all kinds of the defect. In this slide, you can see the easy steel quality inspection. To check steel plate outside by hands, for example, to verify the side cone, the front cone, the length and the diagonal, and check the bottom surface. All of those works are regular and the cost is very low, so we don't need high tech at all. we can let the workers to do this. In this slide, we can see the hard steel quality inspection to check steel plate inside my hands. On the left is a picture of sampling inspection, where it is harmful to steel. The work has to count a sample from the steel product, but the middle and the right is not harmful. In the middle, we can see, I can play. In the middle, we can see a wave when there is a hole inside. However, these two methods are slow and could only detect fragments, and not the whole steel in real time. Okay. To fix that problem, AI, especially computer vision, CV, step into the spotlight. We can see a scan, a device using Python labs to check the steel surface. We must admit that it is fast enough, but not precise enough. Often miss cracks as a whole. A company named Huayuan 计算, we can call it UNIDT in short, contact Dr. Wang last year. It is a large high-tech company in Shanghai. They heard Nars many years ago and appreciate Nars very much. They hope we can use Nars to infer those missed cracks based on their CV results. Well, now, at part 3, we propose an application model for OpenNars. In the right, there is a picture telling us how steel crack detection machine works. Camera is fixed and the steel plate moves upwards. The machine scans downward. In the left, it shows the data format. Our task to infer the white books should be a red box. To apply Nars in a SAI way is a big challenge. In order to successfully complete the task, we must follow some steps as below. Firstly, S0, we need to customize the Nars system since the specific application requirements don't rely on the openness of Nars. We will have to separate out the functions from layer 1 to layer 6, rebuild it into a inference tool. Secondly, we need to transform the representations, which means turning or redefining domain problems into inference problem. Thirdly, we optimize the inference rules, keeping only the necessary ones for the current application issue. Then, refine the control mechanism, which involves transforming domain process into process control and its guidance mechanism. And at last, as for optimize the memory system, build a configurable memory that includes both static and dynamic memory areas. Place domain knowledge in the static memory area, which remains unchangeable. this part 4, or solutions for more open-NAS applications. In this side of part 4, we used Python to rewrite layer 1 to layer 6 of Nars, and reserve the basic control mechanism and the core inference rules. This new Nars version has 4 parts: inference, analysis, storage, other parts retain the native attributes of Nars. Here, therefore, principles we should obey for NAS application. Principle 1 is to transform domain problem into logical problems in order to ensure the direction and the efficiency of inferences. Otherwise, NAS would meet lots of invalid information that will be inefficient and time-consuming. Principle 2 says that NAS would be provided with sufficient domain knowledge, like training of human workers. Domain training or for NAS is necessary, which can improve the accuracy of reasoning. Principle 3 emphasizes that NAS couldn't deal with math problem directly, so math problems should be excluded. Principle 4 means that if we have to do a math problem, we should use tools like Math GPT. As mentioned in Principle 1, the transformation of domain problem into logical form. Here you can see we converted the still correct detection problem into a logic form of anchor points and password. After receiving the still surface matrix, NAS performs a feature scan from top to bottom and left to right, taking the initial bad points as the anchor point. After searching and determining the state of the grid points in the 8 surrounding directions, the next anchor point is set as nearest bad points for past work, and this process is repeated. After Nars travels all the crack points, we can use paths to represent all cracks. So Nars needs to continuously jazz the next bad point after the anchor point. And this behavior pattern is similar to that in human games like Go Bang. We can use Go Bang game to solve the still crack detection. As mentioned in Principle 2, Nars needs domain knowledge. Here, we provide NAS with 3 types of domain knowledge specific to the task: grid point state, direction, and continuity definitions. Grid point states refers to the specific situation of each grid point, namely whether it's a bad point and what kind of bad point it is. Direction refers to the positional relationship between the current anchor point and the next anchor point. Continuity definition refers to the continuity of the current work path of the NAS. We can say grid point 3, 4 is the first byte point. So we can base it to get the surrounding grid point states. Then, based on the initial anchor point position, Nars will search the next anchor point and find the direction between the 2 points. It is a bit hard to understand. In the first sentence, Nars could use two types of information to get one continuity relation. In the next sentence, Nars could use three types of information to renew the former relation. Finally, we can lead Nars by asking questions about the relationships of grid points. We can also inquire about the state of the crack. In this slide, we can see the inference result of our Nars. It can meet the company's requirements. We have also compared our Nars with other Nars. As shown in the picture, the speed has been significantly improved. It can meet the time requirements for specific tasks in industrial tasks. We designed an experiment. We classified combinations of rules to execute the same 5 inference tests. Task 1 is very easy, contains only one variable. But task 5 is very hard with 5 variables and needs a lot of steps to get the final answer. We can see clearly. The results shows that when the task is becoming more difficult, we only spend very little time to finish the same task to beat the same answer, and it is stable. This is really good news. But in the next slide, we can see when we reduce the rules, inference time is not stable anymore. Sometimes it's less, and sometimes it's more. So, in short conclusions, customized Nars is working well. Delete the unnecessary inference rules can make the system more efficient. And weak inference rules, like invisible glue, make the system more convergent. Our future work is fluence. We expect they will be very useful and efficient. Okay, that's all. Thanks.
Okay, thank you
Hello.
for your presentation. Hi, can you hear me?
Yeah.
Can you hear me? Yeah. Thank you for your presentation. And yeah, it's an interesting work. So, any questions for this talk? Okay, so there are no questions in this room. Okay, so I think we have all speakers finished their talks, and it's a great experience here in person and virtually, and the talks are very great. And yeah, and we have seen the the recent progress in in Nars, which I think is a research field, and yeah, we have different researchers from all over the world, and yeah, so I think the next session is general discussion, and we can just there's no special topic, and we can discuss anything we want. I think, let me see who is still in the Zoom room. So yeah, Pei is still here in the Zoom. Hi Pei, do you have anything to share or talk?
Thanks for all the great presentations. There are a lot of things to be discussed, but I'm afraid that everyone is already quite tired. So I will not torture you with my questions. I think we will still have a lot of chance in the future to discuss all the projects.
Yeah. But do you think we can end the workshop now, or just?
Yeah, if there's no more questions.
Yeah, okay. So, okay, we don't have any more questions. So, yeah. So thank you for your contributions and the talk, and thank you for listening. Yeah, thank you very much. So, yeah, it's the end of the workshop. Thank you.
2024. Yeah, 2024.
Awesome.